Okay, hello everyone. So thank you for joining us on this Sunday. So my name is Henry. I'm from Polytechnic Montreal in Montreal, Canada. So I hope you and your loved ones are doing well during this COVID period. Okay. So now I'm having a brief introduction to this event and today's program. So first of all, so we have a Slack channel. So make sure you are like, so you enter the Slack channel so you can ask questions, join our discussions. Because we don't have this room chat, is disabled. We can only discuss in text in a Slack channel. Okay. So if you're a speaker, so we encourage you to share either your paper or your slides in the Slack channel. Okay, so other people can look at them and like have discussions. So during the speaks, we will also have live questions. So you can either raise your hands or like you post your question on Slack. So we will relay your questions to the speakers. Okay, that's some logistics. So this event is co-located with ICPE. Initially, we were thinking about in-person event. So the local organizers of ICPE even planned an interesting one-day trip, so including visiting the Great Wall and the Forbidden City. And most importantly, see the lunches included, right? So, however, when ended up have this virtual event. When you are either give a speak or like you are asked questions, you can tell us, so where are you? So we can have some kind of a physical connection, okay? So here, so this is our organization team, okay? So we have Alexander from MongoDB, Nima from Taylor's Communications, and myself from Polytechnic Montreal. And we also have a list of programming committee members. So they are Andre Bundy from Software Performance and Scalability Consulting LLC, Wei Yishang from Concordia University, Peter Chen from Concordia University, Jerson Sangye from University of Land, Anthony Avantis from University College Dublin, Jinfu Chen from Huawei, Jack Zhang from York University, and Claude Long from HPE, and Liao Lizi from Concordia University. So next is our program overview. So today we have in total 5 sessions, and each session will last 1 hour. Okay, so we have 2 keynote speakers. So they are Jianmei Guo from East China Normal University, and Andre van Hoorn from University of Hamburg. And this year we accept two types of submissions. So one type is research paper, the second type is abstract for presentation. In total, so we accept 2 research papers and 4 abstracts for presentations. So we have 6 presentations. Each one will last 20 minutes, and we have 2 sessions for this, so 2 hours, okay? And we will have a special panel discussion on performance education and training, so which will last 1 hour. So you can find the detailed program on our website. So these are keynote speakers. So first keynote speak from Jianmei Guo from East China Normal University. So his topic is from spec benchmarking to online performance evaluation in data centers. Our second keynote talk is by Andre van Hoorn from University of Hamburg. His topic is architecture-based resilience testing and engineering of microservice-based software systems. So without further ado, we will have our first keynote speak. So First, I will have a brief introduction to Professor Jianmei Guo. Professor and Dr. Jianmei Guo co-directs the System Optimization Lab in the School of Data Science and Engineering at East China Normal University. He received his PhD in computer science in 2011 from Shanghai Jiao Tong University. He was a postdoc fellow at the University of Waterloo and a staff engineer at Alibaba Group. His research interests include system optimization, system performance engineering, and system reliability engineering. He has published over 50 peer-reviewed papers and received one ACM SIGSOFT Distinguished Paper Award and 2 Best Paper Awards. He serves regularly in the reviewer boards or program committees of highly ranked international journals or conferences. Jianmei Guo, do you want to start your keynote speak?
Oh, sure.
Yeah, you can share. Yeah.
Okay. Can you see my screen?
Yes.
Yes.
Okay, looks good. Okay, thanks a lot.
Thank you, Jianmei.
Okay, thanks a lot. Very happy that you invite me to give a talk here. So I would like to introduce some of my work in academia and industry. So basically, I'm talking about a journey from spec benchmarking to online performance evaluation in data centers. Okay, first of all, let me give a lab research overview. So last year, I left Alibaba and joined East China Normal University and co-built the System Optimization Lab, SOL. So we are currently targeting data-driven system optimization, mainly covering a loop of 3 steps. So first, reliable measurement and workload characterization. The second, reasonable analysis and bottleneck identification. And third, continuous optimization and hardware-software co-design. And the entire loop includes many interesting topics. So for example, for measurement, we are currently developing the monitoring, profiling, and tracing tools, and also addressing PMU multiplexing problems. For analysis, we are exploring the iron law of processor performance, CPI breakdown, Amyassen's top-down microarchitecture analysis methodology, and Brandon Gray USE. For optimization, we are working on the compiler runtime optimization, binary translation, heterogeneous programming, and NUMA cache optimization, and so on. So in this talk, I will not cover too many topics. So I will focus on performance evaluation in 2 scenarios. So to conduct a performance evaluation, usually we will set up a system on the test, SUT, right? Mainly including the hardware on the test and the infrastructure software platform, like operating system, compiler, runtime, virtualization, and so on. Also, we will run some applications on the system on the test. Following that, a typical scenario is benchmarking. So we will run a set of benchmarks on the system on the test. The hardware we care about might be a new CPU or a new server. So this usually happens in a small-scale testing environments, right? Another scenario is online evaluation. So we will run diverse real workloads and evaluate their performance in data centers. So here we care about the holistic performance in large-scale production environments. So we will go to some details in the following talk. So part 1, benchmarking. So SPEC is a nonprofit corporation to establish, maintain, and endorse standardized benchmarks and tools. It develops many different categories of benchmarks, like SPEC CPU 2017 and SPEC JBB 2015. And it also reviews and publishes submitted results. Okay, I guess that most of our audience here know SPAKE, so I will not introduce more here. So why we need benchmarking? Because it provides a standardized way to evaluate the performance and the energy consumption for the newest generation of computing systems, like a new CPU from Intel or Ampere, a new server from Dell or Lenovo, or a new cloud instance from Amazon or Google. And we need benchmarking for competitive analysis among different stakeholders, right? For manufacturers, it helps product design optimization for like higher performance, lower energy consumption, and lower cost. And for users, it helps selecting products with higher price performance ratios. Then how to conduct a competitive benchmarking? So here, let's take SPAKE CPU 2017, for example. The basic steps to run it include this. So first, meet the system requirements. Install the benchmark. Determine a switch. For example, we could choose int speed or int rate, flow point speed or flow point rate, right? And then we find a config file and customize it. We can also use the run CPU command and collect the performance results. If we have to publish results on the SPAKE website, we have to adhere the run rules. So the entire process is standardized. The only step relying on users or expert experience is to find a config and customize it. This is also the key to conduct a competitive benchmarking. So to acquire a best known configuration, BKC, the basic steps are as follows. So first, we could start from a configuration A. So it could be a configuration similar to the competitor's baseline configuration, right? Then we measure the performance of this configuration. We change the configuration and produce a hopefully faster configuration, A prime. And we measure the performance of the new configuration. If A prime beats A, then we could replace the old one with the new one. If the found configuration is still not competitive enough, we would go to the step 3. In this iterative process, the key actions are performance measurement and configuration change. In fact, there are many technical challenges for these two topics. And we will just discuss 2 challenges in this topic, in this talk. So the first challenge is the variability of performance measurement. So there are many sources of variability. For example, the running daemons and background jobs, and different thread placement, NUMA binding, or the runtime scheduling, and the multi-tenancy, like JVM multi-tenancy and for containers, right? Multi-containers, a different code or data alignment, enabling or disabling hyperthreading, DVFS, and double boost. So these factors may produce performance fluctuations and make the results unreproducible and untrusted, okay? So to address this problem, one solution is quiescing the system on the test. For example, we could make sure no other jobs are running, and we can use task set or NUMA control to bind the workers to cores or memory nodes. We can also turn off hyperthreading, DVFS, or turbo boost, okay? But in some cases, we cannot build an ideal quiesced system. So sometimes we just want to understand the performance influence of like hyperthreading or DVFS. Then we have to rely on profiling for reproducible analysis. For example, we could measure and calculate CPU utilization of a physical CPU or a logical CPU for to understand the performance influence of hyperthreading. And we can also measure the operating frequency to check out the impact of DVFS or turbo boost. And we often measure the CPI to characterize the microarchitecture performance of different workloads, okay? So the second challenge is the exploration of configuration space. So here is a published report of SPEC-JBB 2015. So the manufacturer is Supermicro, and the CPU model is Intel Xeon Platinum 8380, okay? That is Ice Lake, right? So here are two scores. So yeah, here, the two scores, max JOPS and critical JOPS. So both represent the throughput of this Java benchmark, right? So here the final best known configuration specifies many configuration options. For example, here, the hardware BIOS setting, we could disable the last level cache prefetcher and also disable the subNUMA clustering, right? Okay. And here is the OS setting. And here listing some kernel scheduler options. And these are the JVM flags. So we could set the JVM heap size and different GC policies. So here it uses parallel GC, right? And of course, we should also set the SPEC-JBB run properties, like the number of threads and the number of workers, okay? So note that there are many configuration options for each type. And the combinatorics of these configuration options produce a huge configuration space, including an exponential number of configurations. To efficiently explore the huge configuration space and find a best known configuration, a traditional way is to conduct design of experiments. So for example, we could do one factor at a time design, full factorial design, and fractional factorial design, right? We can also try machine learning methods like classification and regression trees, random forests, Bayesian optimization. And a typical machine learning method is to start from an initial sample, and then we could perform resampling to acquire the training set and the validation set. Then we train the model and tune the parameters, and then validate the model and check out if the model is acceptable. If not, we have to generate and measure more configurations and do the training again, okay? So this method are gaining momentum. So more details can be found in our previous publications. Basically, the key idea here is to find a small but representative sample to build the performance model as accurate as possible, so that we could balance the trade-off between the measurement effort for the sample, right, and the prediction accuracy of the performance model. So here I would like to highlight the importance of domain knowledge, such as new architectural features or new instructions. So this is more like a beacon in the dark to guide us to reach the destination as soon as possible and avoid drifting at random, right? Okay, let's see an example we made before. So ARM introduced the large systems extensions in ARM v8.1. So LSE provides a set of atomic operations, such as compare and swap. Most of these new operations have load acquire or store release semantics. So they are low cost. They are low cost implementations. Compared to the previous implementation using the pairs of load store exclusives. So note that ARM processors have a weak memory model, okay? So we know that LSE would benefit the workloads that are highly concurrent and use heavy synchronizations. So this feature can be enabled in GCC flag and MARC, as shown in the example as an experiment of SPEC-JBB 2015 with OpenJDK 11.0.8. And this experiment was conducted on OCI, so Oracle Cloud Infrastructure Ampere A1 instance, okay? And we can see that enabling LSE gains 1.8 times improvements in max JOps and 2.1 times improvements in critical JOps, okay? So when we conduct a competitive benchmarking, I suggest that we should pay more attention to the new architectural features mentioned in the manufacturer's roadmap. For example, here are the ARM architectural feature in new version N2. So there are many interesting features. So like scalable vector extensions, SVE, okay, enhanced cryptography and PMU extensions and bfloat 16 and int8 matrix multiplication. So we have to understand the performance influence of these features on our applications and guide our configuration optimization. So to summarize, I would suggest a combination of design of experiments, machine learning, and domain knowledge together to explore the huge configuration space efficiently and find the best known configuration, okay? So part 2, online evaluation. So last year, IDC forecasts the whole cloud spending will surpass $1.3 trillion by 2025, while sustaining a compound annual growth rate, CAGR, of around 17%. The as-a-service segments of cloud computing, combining the shared cloud as a service and dedicated cloud as a service, okay, will account for the majority of all cloud spending throughout the forecast. So growing from around 56% to 64%, and with a 5-year CAGR of around 21%, okay. So that is a big marketing. And data centers have become the standard infrastructure for supporting cloud computing and internet services. So let's recall this figure. So different from traditional benchmarking, when we conduct performance evaluation in data centers, the system under test is not a CPU or a server, but an entire data center. And the test applications are not fixed benchmarks, but a large number of different workloads. So in such a scenario, why do we need online evaluation in data centers? So first reason, we do want to know the performance influence of real workloads. However, benchmarks may not represent all real workloads. Moreover, real workloads in production may change frequently. So it is very hard to build a suite of benchmarks to represent all workloads accurately and timely. So second reason, the data center is huge. So usually containing hundreds of thousands of servers or over 1 million of servers. So it is infeasible to build and maintain such an environment with the same size just for testing. So that is too costly. So that's why we need to do performance evaluation online in production data centers. So online evaluation is crucial for the key decision-making in data centers. Due to the large scale of data centers, even 1% performance improvement or loss really matters, okay? So first, capacity planning. So take e-commerce industry, for example. If we plan to increase 27% total sales next month, or next big sales like Thanksgiving, okay? How many servers should we prepare in advance? And how do we plan the capacity for each application? Second, as data centers grow in size, each upgrade to the software or hardware becomes costlier and riskier. For example, here, we may consider the CPU upgrade among different instruction set architecture. We could choose x86 or ARM server CPU. For operating system, we could choose Red Hat Enterprise Linux or Ubuntu. And for compiler, GCC or LLVM, right? JVM, OpenJDK versus OpenJDK, or Oracle JDK versus OpenJDK. So in short, reliable performance evaluation for a given upgrade facilitates the infrastructure optimization, stability maintenance, and cost reduction at the data centers, while erroneous evaluation would produce misleading data, wrong decisions, and ultimately huge losses. Okay. So it is very challenging to conduct online evaluation in data centers. So let's compare the benchmarking to online evaluation and check out the challenges. So first, we conduct benchmarking in small-scale testing environments, so usually including 10 to 100 servers. Okay, while we conduct online evaluation in large-scale production environments, usually including 1,000 to even 1 million servers. Second, benchmarking evaluates a fixed set of benchmarks, while online evaluation evaluates the real workloads running every day. And these real workloads cover different application domains, like e-commerce applications, big data processing, and database. Okay, even in the same domain like e-commerce, there might be thousands of different applications running in data centers. Third, benchmarking usually have a fixed system on the test, while online evaluation has to consider heterogeneous hardware. For example, x86 or ARM servers, RISC-V devices, and GPU or DPU, and so on, right? And fourth, benchmarking usually has a fixed best-known configuration and a set of run rules, while online evaluation may have to consider the different configurations, even for the same application. And these configurations may not be the best-known ones. And also in production data centers, so there might be different DevOps policies. For example, we may use workload co-location. So just co-locate different applications in the same servers, right? To improve the average resource utilization of data centers. So due to these differences and challenges, the key problem for performance evaluation here is, do the effects observed from small-scale benchmarking really scale to the production environments in data centers? So to address this problem, Google proposed the WS meter and the GWP platform. So for example, in the top left figure, so they would like to evaluate the performance impact of a new DVFS policy on over 1,000 production jobs, okay? So in the entire data center, the policy does benefit for some applications, but not for others. Also, the benefit effects are different for different applications or jobs, okay? So to make a holistic performance evaluation for all applications, because the decision maker just want one number, okay? So they designed the WS meter based on each application's IPC, so instruction per cycle, and their quota weight. So note that this work has to collect the microarchitecture data like instructions, so that they have to rely on the Google-wide profiling GWP platform to conduct online profiling in production. Okay. So Alibaba also proposed the RUE, RUE, and speed. So this is a joint work that previously I collaborated with partners at Alibaba and Intel. So speed platform has been used in data centers. It has 4 steps. Okay. So first, estimation. So we collect the performance data and understand what happens now in the data center. And second, evaluation. So we design algorithms and calculate key metrics to evaluate the influence of software or hardware upgrade. And third, decision. So based on the first 2 steps, so we will make decision and determine what will happen in future. Okay. And fourth, then we check out the real effects and validate the results of previous steps like decision, evaluation, and estimation, right? And the key metrics are the resource usage effectiveness, RUE, RUE. So it is defined as the resource usage per unit of work done. So the numerator, resource usage, so collect the resource usage of CPU, memory, storage, and the network. And it was collected by system tools, right? Using like SAR, some monitoring tools. And the denominator, work done, are workload specific. So they would just record the application's completed queries or tasks. Okay. So here I would not like to compare the 2 business products. So since I'm back to the university, so let me just discuss some common topics from a neutral perspective. Okay. So here is a sample system architecture for the data center online evaluation. So on each server, we could set up a monitoring agent to collect the performance data. And all data are integrated and stored in a data warehouse. The analytics engine will implement the key algorithms and calculate the holistic performance metrics. Okay. And then the output data will create a service and serve the users. Okay. So there are a few design principles and trade-offs we have to consider. So first, for measurement, we can use either lightweight monitoring or medium weight profiling. This depends on application requirements. So for example, if we would like to analyze IPC, right, we have to conduct profiling and suffer from kind of high measurement overheads. Otherwise, we can choose monitoring. But in this way, we cannot collect microarchitecture performance data completely. Okay. Second, for deployment, so we can choose either non-intrusive or intrusive way. This is critical for cloud users because some cloud users may have their own dedicated cloud environments, and they may not want to use any intrusive way and install any extra monitoring or profiling tools. So this might impair some algorithms depending on those key data relevant to user profiles, right? But the user do not want to share this private data, right? Okay, third, for data sources, I suggest that we could combine performance metrics and behavior logs to build a comprehensive foundation for performance evaluation. And in the end, for data analysis, again, we should depend on not just AI or machine learning or data mining techniques, but also domain knowledge, because current online evaluation in data centers has a big impact it may influence a huge number of servers. And we have to make sure our evaluation results are reliable enough. In fact, even a low false positive rate could just break the deployment of this platform because the users will not believe the results. They do not want to use it, right? Okay, so now let's take a look at some case. So this case is a CPU upgrade for big data processing platform. So for example, we may want to upgrade the CPU from Intel Skylake to Ice Lake. And we wanted to evaluate such a performance upgrade, such an upgrade, the performance impact of such an upgrade on our Hadoop platform, okay? So in benchmarking environments, so we could first set up a test cluster of around 10 Skylake servers, right? That's in testing environments, and run TPC-H or TPC-DS benchmarks. Then we measure the job completion time or the job resource usage of CPU or memory. So this is kind of a typical benchmarking scenario. Next, we switch the entire test cluster to 10 Ice Lake servers, still run the same TPC benchmarks, and measure the same metrics, the job completion time or the job resource usage, okay? So by comparing the metrics, we could evaluate the performance of Skylake or Ice Lake servers on the Hadoop platform and decide if we were to make such a CPU upgrade. And of course, so when we make such a decision, we can also consider other factors. So like the price quotation of these two types of CPU, right? And all the server and all their energy consumption, right? So that is a trade-off between performance and these factors. In online evaluation environments, so we evaluate real workloads, and the production clusters may have 1,000 Skylake servers. As said before, so it is infeasible to replace all Skylake servers and buy 1,000 new Ice Lake servers just for testing, right? So because here our evaluation goal is just to determine if we need to buy many new CPU and new servers and deploy them in data centers, okay? So usually we conduct a canary release in production cluster by moving the Ice Lake servers to the production environments and generate a hybrid cluster of 1,000 Skylake servers and 10 Ice Lake servers. A non-trivial problem here is that the real workloads here may change frequently. So even for the same application, right? We cannot guarantee the running jobs are always the same. So here, let's simplify it. So we could assume that every day's combinations of running jobs roughly keeps the same. So even though we can choose some comparable jobs, okay, the key problem here is that the typical performance of metrics like job completion time or job resource usage do not work here. For example, the current job completion time was acquired in the hybrid cluster of both Skylake and Ice Lake server because all of these servers just deployed in the same cluster, right? Okay, and the job would just break down to different tasks and instances and distributed in this cluster. So we cannot distinguish how much time on Skylake and how much time on Ice Lake, and thus we cannot conduct a fair comparison. Okay. So that's why we need new evaluation metrics like Google WS meter or Alibaba rule. So we could break down the job into many smaller tasks and instances. That's MapReduce model, right? And then we measure the resource utilization per unit of work done, or IPC, on different servers in production environments. In this way, we are able to still use the same metrics And so in production, right? And evaluate the performance of Skylake or Ice Lake server on the Hadoop platform, and decide if we were to make such a CPU upgrade. Okay. Okay, so the previous case is about hardware upgrade. So now let's look at another case about software upgrade. Okay. So for example, we may want to upgrade the JVM. So that is a kind of infrastructure platform, infrastructure software, and also is required for running Spec JBB 2015, right? Okay, so let's use that example. We may want to upgrade JVM from JDK 8 to JDK 11, and we want to evaluate the performance impact of such an upgrade on our Java applications. So in benchmarking environments, so we usually set up a test container to run Spec JBB 2015 and test the server-side performance of Java application, right? And for comparison, we will set up another test container and using the new version of JDK and running the same benchmark. For performance evaluation, we can measure the throughput metrics, requests per second, or the response time per request. So in such a scenario, we compare the performance metrics per container and per moment before and after upgrade. Okay, this is also a traditional way of performance evaluation in current monitoring system. So in current monitoring system, they would just draw the figures, right, and draw some curve, and then compare this curve, and all compare the performance values in different moments. Okay, that's a traditional way. In online evaluation environments, so we evaluate real e-commerce applications and use the real requests. So again, these real workloads may change frequently, right? And we cannot guarantee the running workloads are always the same. So here we assume that the simultaneous requests for the same applications are the same. Okay. And again, a cluster in data center may have 1,000 JDK8 containers. That's all previous containers. And it's usually infeasible to replace all these previous containers with the new ones. So we still conduct a canary release by adding new containers in the production environments. And that's generate a hybrid set of 1,000 JDK8 container and 10 JDK11 containers. Okay. So for performance evaluation, we still use through the same metrics. So the request per second or the response time per request. But the key difference here is that we can conduct aggregated performance evaluation per set of containers and per duration. For example, we could use all data of the 1,000 JDK8 containers as a baseline and compare it to the new data of all 10 JDK11 containers. So this way, so to mitigate the fluctuation of performance data per moment, so we could also aggregate the performance data per duration for a more robust and reliable comparison. Okay. Okay, to summary. So basically, I'm talking about a journey from spec benchmarking to online performance evaluation in data centers. So benchmarking facilitates standardized evaluation and competitive analysis, right? While online evaluation helps capacity planning and hardware and software upgrade in data centers. And technically, benchmarking needs to consider the variability of performance measurement and the exploration of configuration space, while online evaluation has to consider a reasonable design of holistic performance metrics, so across different application and different hardware. So both are important, okay? Both benchmarking and online evaluation are important, and they just used for different scenarios, okay? So that's my talk today. Thanks. I think I can stop here for any questions.
Thank you, Jamie, for your great talk. Very interesting talk. If you have any questions, please you can either post your question on Slack or just raise your hand. We will ask you to ask the questions. Okay. Yep. First, I will have a question. So the metric, the rule metric is very interesting. So basically, so you have the number of the resources divided by the number of requests. So you can ask, so how do you handle the different types of jobs? For example, you can have a heavy job, you can have a lightweight job, right?
Right. That's a good question. So actually, that's also a key challenge. So when designing this metric, right? So that's actually a key difference between WS meter and rule, because we know that IPC is general to all workloads, right? Because if you just measure the instruction or cycles, it works for all applications, right? Right, so that's not exactly the same, because they are different. So even instructions are different across different ISA, so instruction set architecture. So there's no perfect combination. And when we do using the other way to design another metric, right, like rule. So I think that we wanted to represent the user requirements, because we want a user to understand what we are doing, because they have to understand. So the performance metrics, so what are the performance metrics, what are the results would impact my business. So they wanted to know that your results were relevant to my business goal, because the throughput, right? So the throughput metric is request per second, or queries per second, or tasks per second. But IPC cannot represent that. So we have to represent that. So that's why we designed that. But we cannot combine all different applications. So that combination or that approximation has to be done in a limited scope. Okay. Yeah.
Okay.
Yeah. So I hope I answered the question, but I did not touch more details, because we are so when I moved to university, I'm also working on another methodology, actually already applied for a patent, but I wanted to later publish a paper.
Okay, so basically the users of this metric, they need to define how to use this metric based on their specific scenarios. Is that right?
Yeah, exactly.
Okay, yeah. So any questions from the audience? So we have a question from Slack by Marcus Wasak. Hope you pronounce your name correctly. So the question is regarding benchmarking JDK 8 to JDK 11. Can you tell more about how to compare results before and after adding JDK 11?
Oh, okay. So I think that's probably is from industry, right? They would care about that, because that's a common scenario for Java applications. We know that the previous applications, so JDK 8 is very popular. So many Java applications use JDK 8, and there are many customized, work on JDK 8. But so I think the key, motivating factor is because of ARM servers. So when we have to switch to ARM servers, we wanted to we have to switch to ARM JDK 11. So then we have to consider that, we have to compare this to, platform. Even though your application have to do more customization, you might have to choose this, switch, right? So that's why I think, this question is very great. So that's is also needed in current scenario. And how to do that, I think, it's just like, the slide show. So that's very easy, because I think we just, so you could think that the system on the test has two layers, as I show in the figure, right? Because here you could just fix the hardware on the test, like some server or with like CPU, right? And you could build a baseline environment using JDK8, and then build and you have to use you could use the same server, right? And you can use another new server, and then use a new version of JDK like JDK11, and you have to run the same benchmark like spec JBB 2015, right? That's the first thing, because benchmarking is still needed. So you can run the same, you using the same hardware, using the same benchmark, just change the JVM. And of course, you have to, you would make sure the operating system is also the same. The key, I think the key problem here is that, some applications, if you have to go for some real workloads, real application, you have to do more customization for the new version of JDK. Because previously, some Java application may have, maybe able to run in JDK8, but they cannot run on JDK11. So then you have to do some customization. But this customization would change the performance a lot. So if you do a good implementation, the performance is good. Otherwise, the performance is bad. Okay. So I hope I explained the scenario.
Okay, thank you, Jamie. So we have a few other questions. So I want to, another question is by Carrie Williamson. The question is, can variability also arise from the network effects between the client and the data center? For example, RTT, bandwidth loss. I think basically is how the variability in the network can impact the performance, benchmarking performance testing. All right.
Wow. Okay. So IDT is okay. So it's maybe from Intel. I don't know. So yeah. So yeah, IDT technology is a very nice nice thing, right? But it has some bugs. Okay. Right. So when we wanted to tune, monitoring the cache like CAT, right, or MBM. So we wanted to monitoring the memory bandwidth or the cache tuning the cache size. But and I think is there are some bugs, and we can work with Intel. Currently, the new version already fixed some bugs, but I think we do want to we can use benchmarks to check out the effects of these technologies, because you could just fix some size of cache, right? A fixed size of cache, last level cache for some application, use the remaining for other application, right? But the key point is that so everything is good in benchmarking environments, but it may change when we switch to the real workloads. Because benchmarking, we can always do a good solution, right? And set a good, ratio for cache control or memory bandwidth control. But if we have to switch to the real workloads, we have to consider, because there are many different real workloads. So practical way is to just consider some critical applications. So that's my suggestion. Yeah. But you cannot, make out a perfect solutions for all workloads, because currently, as far as I know, so IDT couldn't do dynamic changing, right? So you can do that, but that would, so the response time would be, so that there might be a huge latency there. So I hope answer the question.
No, I think you actually missed the point of the question. I was asking about internet latency effects on performance, but maybe you can answer that in chat. And I know David and others have questions, so go ahead with David's.
Oh, okay. So, okay, I probably missed that. Right, yeah. So you mean that the internal, could you just explain again? Yeah.
So if you're in, let's say in Beijing and accessing the data center, or if you're in Toronto and accessing the data center, you'll see different round trip latencies.
Yeah.
Can that affect the performance of an application?
Oh, okay. So I think previously yeah, that's a good question. So, but I did not deal with that. Yeah. So previously we that it's a hard question actually, and we normally would just do for one data center, right? And for synchronize between two data centers, we normally would just deploy different workloads because we would check out the customers. We wanted to move the applications close to the customers. So we could do that analysis, but I think here when I talk about the speed and the data center performance evaluation, we care about the hardware or software upgrade. I think your point is about if we wanted to move some, like, you plan some applications closer to users and, just like to make an optimization for the data center, right? So I think that's a different topic.
Thank you very much, Jamie. And we have other questions from David, from Ram, but we are running out of time. I hope the discussion continues in the slide. Okay.
Yeah. I will check out in the slide. Okay.
Yeah. Thank you very much. So our next
You're welcome.
Thank you very much for your skill speak and answering questions, Jamie. So our next session is so we have it's a 3-paper presentations. So our co-chair Lima will moderate this session.
Thank you, Heng. So as our first speaker, we have Thomas Duhlmann. Please correct me if I'm not pronouncing your name correctly, from University of Stuttgart for CTT, load test automation for Tosca-based cloud applications.
Yeah, thank you. The pronunciation was pretty good. I just tried to get my camera working, but currently does not want to. Ah, okay, this way. Okay, so can I start? Can I?
Yep. So just a reminder, you have 15 minutes, and then we have 5 minutes for Q&A.
Mm-hmm. Sure.
Yes. Thank you.
Second. Okay, great. Can you see my screen?
Yes.
Great. Okay, then welcome to my talk about load testing automation for Tosca-based cloud applications. This whole thing was developed and researched within an EU project named Radon. I will add some more details on that, but that's also one reason why we are quite a wide variety of institutions that took part in this. But let's go ahead. So why are we doing this? So what was the reason that we worked on this? First of all, as probably all of us know, that testing is a quite prevalent quality assurance technique in practice, and also a part of software development lifecycle that is quite essential. And in the respect of the project that we worked in, it was about cloud applications of different kinds. And there we saw that it's at least of an equally high importance in that context. And in that context, our aims were to provide a tool support for something that is model-based, so you can reuse things and use also established standards. So we wanted to try to provide tool support for model-based cloud application testing, so everything that is related to the cloud. Have a good integration with typical workflows and applications like IDEs and continuous integration and continuous delivery. And a very important point was extensibility. And for that reason, we worked on the so-called continuous testing tool. To give you a bit of foundations and background, The model-based standard that we use is called Tosca, which is a YAML-based standard for describing cloud application deployments. It is vendor and technology agnostic, so you can extend. It is also quite extensible, which we made quite some use of, and it can represent topologies, so really deployment topologies. So you can model your whole application from an application level to a server level, so where things are deployed and how they are related to each other. And the project that we worked on where this was part of was Radon, which aimed to have a DevOps framework for building on top of these Tosca models and extend these Tosca modeling capabilities to achieve a development framework, including an IDE for developing such cloud applications, and that there this CTT application was a part of. And yeah, model-based software development, this ecosystem was the IDE I was referring to. And this whole thing was supposed to be about all kinds of levels of the deployment and development. So application modeling, deployment, quality assurance, and operations. And those that were to be supported there were software developers, quality of service engineers, and release managers. Now a bit more to the continuous testing tool. So the whole workflow includes the definition, generation, and execution of tests of application functions, data pipelines, and microservice. So function as a service, data pipelines like Apache NiFi, or microservices of all different kinds. And in the whole workflow, we aim to be in several places in the workflow, which includes the planning, the continuous integration itself, and then in the end also get continuous feedback and include that also in the planning for the next iteration. To give you a bit more hands-on information what that looks like, in the context of the project, we had this Tosca modeling tool, which was called GMT. And there you could develop your infrastructure or your topology in a graphical modeling tool, which is GMT standing for. And there we have a simple example to demonstrate this. Maybe some of you know this SockShop example application for microservices. And here we have a very simple one, which is where this SockShop application is hosted on a workstation. And there's a so-called test infrastructure. So we have two elements. So first we have the system under test, SUT, which is the SockShop or whatever application you want to have. And there's the test infrastructure, which has the tools and tooling for running a test against another system. In this example, it's a workstation which has Docker on it. And in there we have a Docker container that has JMeter and several other tooling to run the tests. So it's like a JMeter node deployed somewhere. And the good thing about this separation is that we can reuse these test infrastructures and can also customize them and switch out one part or the other easily. And then the interesting part about this testing thing, inside this graphical modeling tool, we can define different kinds of tests. In this example, we have several tests that we also have in CTT, which is a ping test, like for availability, HTTP endpoint to test that the right response code comes from an HTTP endpoint, or JMeter load testing. And there, for these load tests, we can define some properties like the destination, like the JMX file, so what we want to actually test, so a test plan. And there we also have this reference to the test infrastructure. So these two parts are linked together. So we have like several artifacts, including the system under test and the test infrastructure, that define what we want to use for this testing. And then we have an overall workflow that includes most of these aspects. But to also go back to this integration, we have in this tool, we have two kinds of integration. One is API based, which is used, for example, in this Radon IDE by using a plugin that uses an API to run CTT from the IDE. And we also have a command line interface tool, which can also be controlled, which also controls CTT that way. So that was the idea, to have it easily included into continuous integration, for example. But now to the more interesting part. So how does it work? So I previously talked about the Tosca artifacts. These are these so-called Caesar files and some additional files that you can provide, like credentials and other properties you want to dynamically insert in such tests. This makes it also easier to switch out parts of these tests without rebuilding everything from scratch. And now to the process. So if CTT is executed, it first starts by creating a project, which means you can, for example, refer to a repository, which can hold, for example, these artifacts that we listed on the left. And extracting these artifacts, it collects and puts together all these artifacts. And based on these, an automatic deployment is triggered of both of these parts. So that means for Tosca, there are so-called orchestrators that can actually execute these models in terms of running and deploying these things, for example, on AWS. And after the deployment, we trigger the test from this test infrastructure, which executes the test and then eventually collects the test results. And based on that, we can either report the results immediately, or then based on the results, run some analysis or even update the test plans. And to evaluate this, we have two different evaluations. So first of all, we have the DevOps-oriented load testing that was using AWS and DynamoDB and Lambda functions, an application that is called To-Do List API, which is a function as a service-based to-do list service that we used over the time of our development as an example application. And we have a JMeter load test against these endpoints. And the deployment and everything and the execution of CTT was done by using the CTT CLI. So we could easily run these tests one after the other to have some representative numbers. And parameters for this application or for the tests were the number of parallel users. And we have had another variable about auto scaling for the database. So for DynamoDB in AWS, you can set scaling to be enabled or not, which was a nice example of something that could, even in the cloud where in theory everything is scalable, this would be one of the parameters that even you as a cloud engineer maybe could misconfigure or wrongly configure. So this is an example for such things that could also go wrong in AWS configuration. And after that, we used the results to analyze them using the PPTEM approach, which is analyzing based on domain metrics per workload level. And we have some plots here about our evaluations. So we have the failure rate on the y-axis, and on the x-axis we have the users, and the left one represents the values for database scaling disabled, and on the right side with database scaling enabled. So we can see that at some point, at some level of users, you see that the failure rate goes up because there's no more capacity. On the right side, you can see that the failure rate grows towards the end, but it's still comparably low. And the different lines represent the different endpoints of the to-do list API application. So it creates a to-do, deletes a to-do, and so on. And with this PPTEM approach, we have so-called domain metrics. And based on the results, we could, this black line represents like the optimal values that it should have. And the yellow line in yellow polygon represents the metrics with the database scaling enabled. So it's closer to the optimum, but still not perfect according to this approach. And without database scaling, of course, you can see towards the end, the values go down very low, and it's rather bad results for that. And the other evaluation we did was actually the so-called data pipeline testing. So some of us that worked on the data pipelines module and on data pipelines in the project, and data pipelines are some typical cloud-based resources. And in the core CTT tool, that was not directly included, but this was a good use case to show how extensible CTT is. So they built this data pipeline integration actually as a CTT extension. So to show that we can also not use JMeter and things, but also like any custom thing if you can include into the API of CTT. And in that regard, there were these Tosca models for the data pipelines and the data pipeline test infrastructure. These were developed. And in the end, there were 2 validations to show that this fulfills the requirements also there. The so-called thumbnail generation data pipeline, which had different batch sizes of 25, 50, or 100 images, where images were uploaded to a bucket, which transformed the images to thumbnails and placed them in another bucket. And there the measurements of load times, throughput, and success rate were recorded. And another thing was the transferring data, which is also a typical use case for data pipelines. So to cross the boundaries of services, I was transferring data between AWS S3 and Google Cloud Storage. And there were different data sets where the processing time and the success rate could be measured. And that could be properly done with CTT as well. Okay.
I'm sorry to interrupt, but the time is almost over. Just there.
Yeah, I'm finishing. Thanks. So to summarize, CTT provides means to test different kinds of cloud applications. It has an extensible architecture for adding custom tests. So in our examples, we had load, availability, and data pipeline tests, but as I said, it's very extensible. The result reporting and analysis in cooperation with the PPTEM approach was shown, and also the data pipeline extension demonstrating the extensibility and applicability of CTT in other parts. And that concludes my talk about our continuous testing tool. It's open source and based on this Oasis Tosca standard, and as I said, modular and quite extensible. Thanks a lot.
Thank you, Thomas. A very interesting talk. I believe it is a very important aspect to introduce things like DevOps into load testing. I had, before we move on to the audience question, I had one question. So have you thought about like how we would handle the performance variability in the cloud? Because we know like different instances, for example, on AWS will not perform exactly the same. So how do we basically compare the results and separating between the differences from the cloud and from the software?
So you mean to what extent the cloud resources are impacting, or how much the software is impacting the results, you mean?
Yes, exactly.
I think it's quite difficult, but maybe due to this ability to have this test infrastructure possibly deployed quite close to it. So for example, in the same data center, you could at least reduce the impact. So as the testers, and where this CTT runs is not where this test infrastructure needs to be executed. So that way we can have both things, both system under test and test infrastructure in the same data center, or possibly even deployed on the same VM if you want. I think that would be a possibility to at least reduce the impact, probably not take it away as a whole.
Very interesting, thank you. So we have a question from Alex Podilko. So he says, DevOps load testing evaluation, what exactly made it DevOps? What DevOps specific was there?
Could you repeat it, please?
So DevOps load testing evaluation, what is it, the thing that makes it DevOps? Like, what is it that is specific to DevOps that appears in this tool?
So I think maybe Andre can add afterwards something, but I think it's DevOps because first we can include it in this, easily include it in the workflow by providing these means to have it inside a continuous integration, continuous delivery pipeline, and also parameterize it quite a lot by these artifacts that we have. And in addition, I think because we have these cycles, this would, in my opinion, also qualify as quite DevOps-like behavior. But I mean, Andre, if you want to add something, you can also.
Yeah, I think you already answered in quite a good way. So all this automation is DevOps, but particularly in this domain metric-based approach, we always incorporate the realistic workload from production. So we continuously monitor the system and see how the workload intensities look like in the production system, and then we can adopt. So let's say next Monday we expect the following workloads, and then we can easily check whether our configurations are basically how well they fit to the operational profile that we are expecting. So I think it's both the automation and the feedback from operations what makes it DevOps specific in this case.
Very interesting. Thank you. We are almost out of time. So thank you again, Thomas, for a great presentation. Our next speaker. Thank you. Our next speaker is Alexander Podilko with a review of modern challenges in performance testing. Alex, you can start whenever you're ready.
Do you see my screen?
Yes.
Okay, so I want to talk about modern challenges in performance testing, and because it is just 15 minutes, I just want to concentrate on current trends and industry and academia as I see it. So here I tried to put together the challenges I see as a practitioner and the research I am aware about, which might be pretty limited, and put them together and maybe just to kind of start discussion if we have really gaps there and what they are. So one very interesting research is that a report, a little bit already 7 years old, but there are a lot of interesting stuff there. But for performance testing, I see only 3 sections there, which I discuss a little later. And it definitely not aligned with performance testing because this particular section are in different, not aligned with performance testing. And one thing that I try to do that I upload slides, definitely a lot of slides, and I won't stop on most of them. And I try to put live links in PDF file, you still could click on them and find things that I refer here. There are some surveys around. That is one example. And I found that there is some problem with it. For example, this survey make conclusions that most surveyed companies do not regularly conduct performance evaluation. That is true if we count all companies. But actually, I think the interesting is a company that leads the pack, that introduced new technologies. Yes, most companies don't do anything with performance. A lot of companies still use more traditional legacy approach, but that is not what we actually interested in, because if the performance is not important for them, they probably won't do it. If it is important, they eventually switch to most advanced practices. And what trend I see is that integration of performance engineering, including testing, into agile development, DevOps, and so on, whatever fashion terms are. And I believe that actually defining is agile development. So iterative development when we have something working on each stage. DevOps, I think, actually just one case where it could be used. But terminology is pretty vague here. And my impression that neither tool vendors nor academic research not very supportive of that. There is some interesting stuff, but not actually supporting the whole trend. And why I say that? Because it's from most advanced implementation I saw or heard, mostly are homegrown proprietary solutions.
Probando. 1, 2, 3, probando.
And again, I see that it is a trend. I see that most serious high-tech vendors do have continuous performance testing integrated, although not much information available. That is not something that big high-tech company share, because it is rather support activity, not main kind of activity. So why we need to have performance testing to be continuous? Because cost of fixing defects earlier is significant, and if we catch problem as they happen, it help a lot and simplified fixing them. So, and that change paradigm, that change mentality that you need to do how you approach performance testing, and that is pretty significant change, which are not deeply investigated in my opinion. And then I will go to specific challenges that I see. Again, maybe a little bit random set, other maybe highlights other challenges, but let's just to start. There is a lot of interesting research, and actually a question before about it, how extract workload models. A couple of them mentioned. Important topic, but rather small one comparing. I see it as a larger problem, kind of coverage optimization. What actual test we want to run, because performance tests take a lot of time and resources, and maybe it definitely not viable to run all tests on each commit. So maybe we need some kind of tiered solution, maybe something some tests each commit, some maybe daily test or something, and large scale tests which could be outside of continuous integration. And here we have huge problem, especially for software vendors, which need to test it for different configuration, different workloads, how often you want to run this test, and actually pretty big costs to run this test, to analyze results, cost of running efforts. So we have clear trade-off between coverage and cost. And how optimize it? It is not researched well, in my opinion, because if we address it seriously, we add more and more tests, and it still grow and grow, become more costly to maintain and run. One approach I saw that kind of look if some results are correlated. If some test results are correlated, maybe we don't need to have separate tests for that. Which tests find problems. There is, it was mentioned, for example, in this last keynote presentation at previous load testing and benchmarking workshop, and actually ICP data challenge, which would be later, in my opinion, has some interesting finding about that. Challenge of integration, how we do it. Yes, now there are almost all load testing tools have some kind of integration. CI tool has some support like Jenkins performance test plugin. We have multiple performance testing framework combining different tools. That is one example that, and kind of typical when putting together some database like InfluxDB, Grafana to visualize monitoring solution, but it became pretty complex. And all really advanced system I saw or heard are basically homegrown proprietary solution. Here some mentions of them. As I mentioned, that is live link. If you take my slide, you could go get there. And that is why I'm saying that the actual load testing vendors are not actually up to speed in supporting real continuous performance testing efforts, large scale, because we see that everybody who really needed it implemented something themselves, which of course also very costly. But from another side, they are optimized for their specific solution. It may be actual difficulties here because to make it real large-scale efforts, it should be more specialized. Maybe it is a real challenge to make it generic. That, for example, in bulk proprietary components that use on MongoDB continuous performance testing, and of course there are many parts that are standards, which also mentioned here. Next challenge is challenge of variability, which already was mentioned here. We have problem with environments, we have problem inside system, and there is multiple research and posts which discuss that, how we can address variability. Again, it was mentioned in keynote too, some ways we can address it. Next challenge is change detection, which actually gets some traction in research. Problem, of course, that we have complex results which not easy to compare. But there is interesting work with, for example, in that project, Captain SH providing SLI, SLO as code. And of course, there is multiple research on change point detection, and MongoDB is use e-divisive mean algorithms. Here are some links to it. It looks like it also used at Netflix and some other places, and that is completely open source. So you could also use it. Challenge of advanced analysis. You may need to analyze it further, so keep all artifacts. There is some research interesting about visualization, because there is a lot in data behind some aggregated. For example, we need to look in many cases beyond aggregating for depending on what pattern data has and what best way to visualize it. Challenge of maintenance, again, the same trade-off I mentioned with coverage, but it also depends how you implement it, what kind of interface you use, and what checks you build in. There is some interesting startups and work which try to use artificial intelligence to catch changes in the system, a kind of advertise self-healing scripts. Although I haven't heard that in performance testing, but that might be one interesting direction of research. And then we have change of organization. We have multiple roles, and looks like we are now we don't have well-defined role anymore. So different companies package this role differently. So it looks like we didn't get to standard in the industry yet. So, but we see a lot of different roles, and what would be actual role of performance engineer and team in the future, it's still open question.
Sorry to interrupt, the time is almost out.
Yeah, and finished. So that is also pretty interesting challenge. And who exactly in the company should do maintenance? So basically that's it. So integrating in agile development, I see as a major and the main maybe trend. It looks like tool vendors and academia is a little behind this trend. And I listed all these challenges that I saw. Again, it is not maybe full list, but just kind of start discussion. And if there is any question, I would be happy to answer.
Thank you, Alex. A great talk, like always. So just a reminder to everyone attending, you can ask your questions on the Slack. So before we get to that, I had a question of my own. Alex, how would you say like the difference or the gap between academia, the main ones between academia and the industry is at the moment with respect of performance testing?
That is what I tried to answer by this presentation, because so it looks like some topics get very popular in academia. For example, how to extract workload from logs from other things, how to build model, but some practical questions didn't get much attention. So people address it somehow in industry one way or another, but I think it may benefit from some further research in academia. For example, basically the main problem, which test to run, which and how often, and that basically may be the main question of testing. And I haven't seen much research on that part, but it may be difficult to formalize it. It may be easier to take some smaller task and address it.
Hopefully, with presentations like this, more and more research will get focused on the important aspects of performance testing like this one. If anyone else wants to ask any questions, you can open your mic or type in the Slack chat. All right, so we're almost out of time, so I think we can move on to our next speaker. Just remember that we can use a Slack for if you come up with questions after the presentation is over. Thank you, Alex, again. Our next speaker is going to be Leandro Melendez. Just correct me if I pronounce it incorrectly.
Awesome.
And thank you. And the presentation will be on cost-effective load testing. You can start, Leandro, whenever you're ready.
Okay. Sorry. Let me start sharing the screen. Okay. Can everyone see it?
Yes.
Awesome. Okay. Hello, everybody, and welcome to this quick presentation where I'm going to give you some insights on cost-effective load testing and how money is involved in all these performance load testing, performance assurance, and nice practices. But before I begin, let me talk a little bit about myself for the ones that do not know me. I am Leandro Melendez, also known as Señor Performo in the internets. I am a DevRel, a performance advocate with K6, an open source load testing tool. As I mentioned, I started as Señor Performo from my blog, srperf.com. If you want to go and look it, I have a few blogs where I try to explain lots of things around load testing, performance in general, and some other IT topics. You can find me on all of the social networks as Señor Performo or Leandro Melendez, Facebook, Twitter, Instagram, YouTube. I'm missing one. Okay, any social network almost. I am the host of the Perfights Español podcast, the Spanish version of the Perfights podcast, and I am a frequent contributor in the English or main show for the Perfights family. I started somewhat recently as a performance YouTuber. I have some channels. You can go and learn as well some other performance testing topics. Look for it, Señor Performo, ENG for English, or just Señor Performo if you know Spanish or want to practice it. As you can see here, I like public speaking. I do some presentations here and there, whatever. I get an open microphone to speak and talk about performance and help the world to improve on it. And last but not least, I recently released my first book on performance testing, The Hitchhiking Guide to Load Testing Projects. Step-by-step walkthrough that will help you and learn the principles of performance, or specifically a load test project, traditional load test, with fun examples as a video game with levels. Lots of fun in the book. If you're interested, hope you like it. But okay, enough of me. First of all, I want to thank the LTB conference for giving me this opportunity, and thank for the ones that are listening us. I really appreciate that you're taking some time to hear of the silliness that I'm going to be talking about. But speaking of talking about, I'm going to talk a lot about money today, how it is related with performance testing and specifically load testing. And you may not believe it, it's everywhere. You will probably, as a load tester or performance tester, you are in the backstage, you don't notice some of these things happening in the management side, and you may not be aware. And for the ones that are in management seeing us, I'm going to give some explanations on cost impact, what's the deal with money, and what happens all around it. So speaking of those impacts, let's start with them giving some understanding. What can be the problem with money if you don't pay good attention on your performance and load testing? So the first of all is that Bad performance will give you several kills monetarily. In the end, everything will translate in money, sadly. But what problems, I mean, I don't think I have to say too much about this, that the problems that bad performance will bring, we will have slow systems, they will be intermittent, sometimes they will be available, sometimes they will be available, sometimes they will be slow, sometimes they will be fast, and all this will generate unusability. What does this mean? That, well, we cannot happily use our system. And again, all these situations mean losses, monetary losses. Why? Because we will get frustration. I won't like to use that system. I will be frustrated with it. And if I'm using that system to sell things or services to people, it will be slow to sell those. People won't be able to buy on our sites or on our platforms, or plainly won't be available to buy or get the services from us. And this generates a dislike for our application. Customers won't return. And many say, hey, but I have an internal application. I don't care about customers. Well, you should care about your users and internal employees, because they will be slow to work. They won't be able to work. And you're creating the system to help them to be more efficient, right? So if you provide them a slow system, a faulty, non-performant system, they won't be able to work as good as possible. And they will have all the other things. They will be frustrated, sad, and won't enjoy that system. Because you want them to do work on it, right? So all these, as I mentioned, translates into costs. It costs everything if you have bad performance. Everyone and everything will be affected. As I mentioned, you will have less sales, you will provide less services, you will have to spend lots of money on support, because whenever some performance problem happens in production, we all know, the later you catch it, the most costly in time, money, tears, blood, everything happens here. You'll have problems, but well, mostly money, right? The processes to fix it will be interesting and expensive. And as well, when you have those processes, you may say, yeah, I am in the cloud, I don't mind. Well, if those processes do not perform well and you put them in the cloud, it will be like having an old fridge plugged to your electricity. When the power bill comes, that's when you will wish to have a better fridge or a better powering device at home. The bill can be quite expensive. Be careful with that. So moving on a little bit on the scripting. I mean, this is something that most of us, or probably all of us, are interested in finding out how our scripts can be cost effective, or where are we wasting resources, or how is it that we can avoid this type of problems. So around scripting, let's start with traditional scripts, those that we used to work on and we used to do at a front-end level, end-to-end, lots of steps, or maybe not too many, but there were some steps on them. And those that we were using to generate big load tests. A friend of mine gave me the acronym from a way that I have to call this type of test. Is the BALT, big ass load tests, which are something that we performers like a lot. It's fun. These load tests to test for capacity, to push the system down to its knees. Where we put multiple scenarios. We have the spike, we have the endurance, we have the stress test. And on all of this, in several organizations, when in my consultancy days, sounds like it's far behind me, but it was just last year that I was still providing these consultancy services. I would come and the customers would request, hey, I have 150 business processes. I want you to automate all of them for my load testing. Why? That's not cost effective. That's not very good for you. And I tended to explain this with the Pareto principle. Some of you may know it as the 80-20 rule. It was something implemented by this guy, Vilfredo Pareto, an Italian, I think he was economist or mathematician, or, you know, there are intersections on those. And he came with this saying that 80% of the land in Italy was owned by 20% of the people. And you may say, well, yeah, what does it has to do with my process? What we care the most about with load testing is to simulate load, to attack the processes that generate the most load. So it will be silly or futile to try to focus on scripting the ones that are happening once a day, once a week. I have even received requests to automate the ones that happen once a year, a yearly process. You don't need an automation for that. I mean, how much does it cost per hour of scripter to come and generate that? Rather than just to bring someone that knows the process, come, click wherever is relevant and trigger it. Usually it's way more cheap. So you want to be cost effective. How do we apply this Pareto principle? So we want to have a sample of what is all the utilization, how many actions happen in the system, and then we will have the list of possible actions in the system together with how much each one of them are occurring. We will sort them by number of hits that we will have and try to pick the 80%, which ones generate the 80% of the load. Generally, you will have 20% of them, or even less at times, that are super exhaustive, the ones that are happening the most. Those are the ones that we should focus on automating rather than the ones that happen a few times per day, per hour. The ones that in this example, I have 15 processes. And I sorted by occurrence. I did the sum of all the events and calculated the percentage of each, how much of the 100% each one of them constituted. So when I sum the highest ones, I very quickly will get 80% or more. As you can see, from 15, I came down to only 3. Those 3 are crucial. Those 3 will generate over 80% of your load. You almost have all the load of the system with those. If you want to be picky, you may choose the other 5, but we have like 5 or 6 scripts out of 15. So what I'm trying to say, pick up the ones to generate 80% or at least 80% of the load, and you have the most cost effective. You are simulating lots of load. The other ones, you can bring someone to trigger those processes. What we're thinking here is the cost of the scripter hour, the cost of the execution, against the cost of bringing an expert just to do that click and trigger the process. You can even do it at the middle of your execution. So there are multiple ways in which ones we can optimize here. You have to be wise on which scripts or business processes do you put inside of, and I'm gonna say the K here, traditional load test. These ones that have lots of processes, lots of steps. Why? Because this is for traditional. And I'm telling you right now, in traditional, be picky, be exclusive, the ones that generate the most load. But we have modern scripts, modern systems, modern solutions that are tiered. They have the services, they are agile. Here we have to switch the thought. Many of you may know the automation pyramid. I like to call it the Aztec sacrifice automation pyramid, where we have our tiers. If you know, at the bottom, we have unit testing. At the middle, we have services. And at the top, we have end-to-end. What we traditionally used to do on what I just mentioned is to focus on the top, where it's more complicated, more expensive, and where all the sacrifices happen. And talking about the bottom, there we should have the most coverage. Get some automations. I mean, unit testing should be done by developers. We should have it with every finished process. And do some performance measurements out of them. And we can leverage them to also do some load tests inside of our own system. Those are the cheapest, fastest, easiest to create, maintain, support. So those are the ones where it makes sense to do the most. Have wide coverage. I generally relate them to guacamole. It's not spicy, it's yummy. Have as much as you can. On the service tier, in the middle one, we have salsa. It's somewhat spicy, not too much, so you can be abundant with it. Just don't exaggerate because you can get in issues. On those ones as well, it's very cheap, it's very fast to generate automations and the service tier. I'm gonna do a quick pitch here. K6 helps you a lot on this tier to quickly generate automations, easy, straightforward, hit your service, be done with it, and have a lot of coverage. Almost all of your services try to do the coverage, try to have as much salsa as possible. And at the top, try to avoid the sacrifices. Those are the most expensive, slower, more hard to maintain. And all of that translates into cost, which is a big sacrifice. We don't want to do sacrifices in our load testing efforts. So beware. Be aware of how expensive each one of the tiers and try to do most coverage on the cheapest one. Most organizations try to do it upside down nowadays, still, I would say. So another element that is really important around cost is people and operations. You may not believe this, but we have a lot of intersections between people, operations, and costs in the realm of performance testing. How is this? Let's see. First, the load testing environments, many do not take into account what is the cost of having those. And depending on what is your use, what is the best choice or what you should do. As an example, on premise, the traditional, when we had the load balancers at our basement or in the data center, wherever we had all these machines dedicated to generating load, depending on what was the use that we wanted to do for them, buying them or configuring them, we only had the payment once. But the problem is that the cost for that was somewhat large because we had to buy a decent amount of computers to generate all that, get the hardware, configure them, and after we had them, we had to do the maintenance. These ones were really good at times when we had plans to do long-term performance testing again and another cycle. You did a big investment once, but then you own it and it's just maintenance and you keep going. Understand the costs, understand afterwards what is the cost that you will have on maintaining those, and what happens in the cloud. Where in the cloud, if we send our load generators or just hire some load generators, these type of environments are also good because you can do some quick tests, be done, and get rid of it. Not too much management or hassle around it. But the cost here will be recurrent. You will have your monthly bill somewhat cheaper. It will be, well, way cheaper than buying the machines and having them and managing them. You just pay a rent and you get this service. There's no hardware. You don't deal with too much configuration. And the good thing is that you can just get them on demand. Let's say you have a one-time load test that you need to do. Hire one of these, be done, get out, you're good. So there are balances. And generally, these configurations on the cloud will be someone else's problem. You won't have to configure routers and install them and the software update. No, it's something that ready to go. Just get your test, be done, be out, just pay the bill quickly. So understand those impacts. It's very important because many organizations do not pay attention and just go wild with them. Now, quickly, speaking about tools and the people. Here is a big constant challenge that I always get. What should I pick? A commercial tool that is easier, but it's expensive, but generally promises to be one good tool for everything performance. Or
I'm sorry to interrupt. I'm sorry to interrupt, but the time is almost
running
over.
out of time. Okay, so here quickly, we have tool versus open source, paid versus free. Some are expensive, but easy on people. Some, the open source, are cheap, mostly free, but you need more technically specialized people. Those are the balances. Think of that. You want to spend more on the tool or spend more on the people. Depending on your perspective, there's no good choice. So to close up, make sure to invest wisely. Performance testing is an investment for your application, your organization, and everything around that. It's an investment. Sometimes you may want to do a big payment first and be easy at the afterwards, or vice versa, not to waste too much money, but usually those are expensive down the road. Okay, with that, I want to thank you, everyone, for paying attention. Hopefully you got some insights on where you can be more efficient around money and performance. It's a huge area that you can go over. I'm gonna go now, give some time for Q&A, but before that, if I don't have time to answer everything, if I don't catch up too much on Slack, you can find me on all of the social networks, Señor Performa or Leandro Melendez. Feel free to reach out, subscribe, hit like, all those silly things on the socials. And with that, I will give some time for the good old Q&A.
Thanks, Andrew, for a great presentation. So if you want to ask any questions from Leandro, you can just open up your mic or type in the Slack chat.
Did you ever try to formalize that kind of analysis? So
yeah, we have some examples on what have been the effect of not doing performance testing. The usual, we know some of the millions of dollars lost in HR Block or Obamacare, all those big examples that we know. And there are some others where we have numbers. I have done some presentations where, hey, this is a cost for automating all your 15 business processes. And this is the cost for only this, and bringing a specialist just to click run on those other processes that may be business critical, but they are not worthy of automating. There are several examples. I will be very happy to repeat and give some hard numbers, given the time for this. Try to make it a little bit straightforward.
yeah, if you have it online, maybe you could post it in Slack so people could check.
I don't have it at hand online, but I'll work around it, promise.
Yeah. Thank you.
Thank you again, Leandro. And with this, our time is almost over. So I will hand it to the next session's chair, Alex Podolko from MongoDB.
Yeah. And now time for our second keynote. And I want to introduce our keynote speaker, Andre van Horn from University of Hamburg. He will talk about architecture-based resilient testing and engineering of Microsoft microservice-based software systems. Andre is a senior researcher with Department of Informatics at the University of Hamburg, Germany. Before he worked in many other Germany universities. Andre's research focused on designing, operating, and involving trustworthy distributed software system. Of particular interest are runtime quality attributes such as performance, reliability, and resilience. And he is very active with SPEC and ICP. So without wasting more time, Andrea, it is yours, all yours.
Yeah, thank you, Alex, for the kind introduction. In this presentation, I would like to talk a bit about our work on architecture-based resilience testing and engineering. And I think you see my footer slide. No, that's fine. And this is a summary of a lot of works we've conducted in the past years in several projects. So, and we are still continuing. We just started a new project called Equalizer. So this topic of architecture-based evaluation and also resilience engineering is something we are doing for quite some time already and are still working on. And before I start, I would like to emphasize that this presentation contains a lot of material that resulted from joint work with many others. I saw that some of my co-authors I'm listing here are actually also present in the call. So if we are in the Q&A round, maybe they can help out even better than I can. This presentation is structured in the following way. So first I will talk a bit about the motivation of resilience and transient behavior. Then I will give a summary of the basic things, focusing on scenario-based resilience testing and engineering and some formal method, and give an outlook on current works and tools. So first of all, resilience as a quantitative architectural property. I think I don't need to motivate much about the dependability problems in application systems, because the audience here is well aware of load-related problems that can hopefully be revealed by load testing. But we still know that these problems get into production. So for example, system overload situations where the systems, using some architectural patterns, react in a better or not so good way to performance-related problems. So we can see for example, the waiting room pattern being introduced. Then there are some other examples where systems degrade in a less good way, let's say. So we see standard error messages, HTTP error messages, or other kinds of failure. So there are many dependability related problems. There's a whole set of research that nicely structured concepts and threads and metrics around dependability. And usually what we understand under dependability is attributes, quality attributes such as performance, safety, security, reliability, availability, and also resilience. So what is resilience? Let's look at a simple example on the right side of a service-based system, very typical. We have an entry point with a web UI, a passive management system. So different kinds of components that interact in a certain way with each other. So what does resilience mean? What we can observe very often in these more and more distributed systems is that one or more components fail. So in this example, the payment system, for example. But before that, we can see, or let's look at the way we usually quantify resilience. So we can look at resilience as a two-dimensional graph. So the x-axis is the calendar time and the y-axis is some notion of quality of service. So we abstract from it with some kind of a, let's call it utility metric. So from 0 to 100%, and 100% means that the administrators or the stakeholders of the system are fully happy with the system's performance. This could be that we meet all our performance requirements. So for example, 95% of the time, the response times are below 200 milliseconds. And now what we observe is that systems are affected by different types of disruptions or changes. So for example, in continuous integration delivery scenarios, we see that different software artifacts are getting updated. They have a cold restart, or we have some cold phases where requests take a bit longer. Software versions are updated by versions that have different performance characteristics and so on. We see changing user behaviors. So this could be behaviors in the intensity, so the number of users that are concurrently accessing the system by whatever factors, could be the day of the time of the day, or by some advertisements, and then people rush to the website and want to buy certain products. And finally, we see many failures. So this can be failures in the infrastructure. So for example, virtual machines failing, virtual machine zones, or cloud resources failing, external systems, so for example, payment systems failing, and so on. So modern systems need to be able to cope with these problems. And resilience is usually considered the time-dependent behavior. So coming back to our graph, we can see that the system here is still in 100% quality of service. And then we see a certain type of disruption that I was talking about. So for example, the payment service fails. We go down to a quality of service. So we have degraded quality of service in the system usually. And now we expect the system, if it's a self-adaptive system or self-recovering system, that the system comes back to normal operation, hopefully, by applying some architectural tactics. One of them could be a circuit breaker patterns, and there are many more. I will briefly go over it in a second. And eventually, the system hopefully comes back to a level of 100% quality of service. And now we can analyze the time between being in a healthy state until getting back to a healthy state. And there are many ways to quantify this resilience. So for example, looking at the size of the area of the period. So basically we have some accumulated loss. It could be the total number of requests that have failed, or the total, let's say, delay that has been accumulated over time. And now the goal is to, we all know that there is, in resilience, we do have some loss, but we want to specify, quantify this loss, and want to make sure that the system behaves as expected. So just going a bit more into technical architectural aspects. So again, we see a sketch of an architecture. We can assume that this is, again, an entry point. We have some edge services that talk to some backend or middle tier services. And now one of the middle tier services fails. And we can see that E1 and E2 depend on this service M2. Unfortunately, what we see very often in systems is that we have some so-called cascading failures, which means that if the system we are depending or the service that we are depending on fails, then we see also a failure of the services that depend on that service. And this is one example of a concept called anti-pattern, which means it's a recurrent problem or recurrent thing, architectural tactic we see in practice, but as opposed to patterns that usually are positive. So for example, observer patterns, I mentioned this waiting room pattern, this is has a negative impact on the system. To counteract these issues, these anti-patterns, we can have introduced patterns. One of them is circuit breakers. So like in a real electric circuit in your house, if there's a overload situation in the electricity circuit, we know that the circuit breaker opens to protect the system. And then afterwards, we can put it back if the problem has been resolved. So this works pretty similar, the circuit breaker. So if E1, for example, notices that M2 is not available, it will open the circuit and no longer talk to M2 or talk to some failback services so that M2 has some chance to recover and E1 is no longer affected by this outage. So just to show one example, in systems or today's systems, we know that they are decomposed into multiple services. And this could be one way to implement such a circuit breaker. So we see, for example, one service that talks to a backend service for some special priority customer services. And if this one fails, we see just a simple error message instead of the whole website failing. So I can, if you don't know the book, I can strongly recommend the book by Michael Nygaard on stability patterns and anti-patterns. And Michael Nygaard comes up with this nice taxonomy. So there are some anti-patterns, some consequences of these anti-patterns. For example, cascading failures is listed here. And then, like a taxonomy, how these anti-patterns work with each other or lead to each other. And on the other hand, he also introduces or sorts in these patterns, for example, the circuit breaker. And there we can, for example, see that the circuit breaker works together with timeouts and counters cascading failures, what we just saw in the previous example. So now we could assume that we have everything we need to build resilient or stable systems. And whoever ever used or needed his or her backup, so data backup, when a system, for example, crashes, knows that it's good to have a backup, but you never know whether this backup really works. So it's the same with these resilience patterns. So if there's a problem in production, we never really know whether our patterns work the way they should work. And now, over the past years, there has been a lot of activity in the field of resilience engineering, and it's also called chaos engineering or resilience testing. The question is, how do we accept failures? And the best thing, so there's a community behind this chaos engineering, and they define chaos engineering as the discipline of experimenting on a distributed system. So could happen or usually happens in production, so that you introduce some kind of turbulent conditions on purpose into the system to see whether your resilience mechanisms actually works. And this is based on well-known concepts based on failure and fault injection. Prominent examples are the Simian Army by Amazon, for example, and meanwhile there are a bunch of startups that resulted, for example, they came out of Netflix, who really pushed this topic in the last years, and startups that provide some improved tooling for resilience and chaos engineering. What's the usual concept? So usually you would define some kind of a steady state metric. So this is a metric, ideally on a business level and not on a technical level. So Netflix always gives this example of number of streaming starts per hour, which is how they know that their system is working as expected. So they have a pretty good model that over the day, how many starts of video streaming starts they can expect. And if this deviates, they assume the system is not in a steady state, but if it is, you can make certain assumptions about how the system reacts on different outages in the system. So these are formulated as hypotheses. So for example, if the database or when one of the database nodes fails, then we will be back to normal operation after, I don't know, 5 minutes, for example. So these hypotheses are encoded into resilience tests. These tests are executed. You make certain observations about the metrics of the, so how basically the system reacts to these injections or failures. And if there's an issue, you need to fix the issues and then go back basically to this loop. And you could imagine that this is integrated also into, just like load testing, into your normal operations environment. And where for a load test, you need a workload specification. For these resilience tests, usually you need a specification of the fault, so-called fault load, which means what is the type of failure mode or fault you are introducing into the system at what point in time. And you will see that in our research, we are combining basically load and resilience testing, because if you're not running the resilience test in production, you need some kind of supporting load driver that brings the system into a load situation that fits your steady state assumptions or hypotheses. So what is the challenge? We can observe that systems do still suffer quality degradations from changes causing transient behavior, even though we do have all these architectural toolboxes with patterns how to cope with resilience issues and these changes. Possible reasons that we see and we are working on in our research is that resilience requirements, elicitation and evaluation are not systematic and not conducted. We know very well that this is the case also for more basic requirements, for example, basic performance requirements. We know that they are not very well elicited and specified in practice, and this is even more severe because these assumptions or requirements are not formulated for resilience. Further on, identifying, prioritizing, and configuring resilience tests is non-trivial, and this is also related to load testing, because it's pretty hard to decide what are the relevant load tests that need to be executed. And because it's usually very costly in terms of resources and time, we need to prioritize these load tests. That's the next point, actually. What are our objectives? We want to provide interactive specification and refinement methods for transient behavior that are focusing also on non-experts. So non-technical people that are working on the application domain are able to express these requirements. And we want to come up with quantitative evaluation methods for transient behavior, always with a combination of model-based approaches and test-based or measurement and experiment-based approaches. What we can see, so this is some kind of a framework. We have the changes that impact the system. We have the architectural concepts that shall counteract the resilience. For example, architectural reconfiguration, transient behavior coming into the system. And then we know very well that there's a lot of research already on formal analysis, how to analyze reliability and resilience concepts. And now our idea is that we want to come up with supporting tools for non-expert stakeholders, so architects, developers, customers. Of course, developers are experts in their field, but very often they are not experts in resilience engineering or performance engineering. And here we work with, for example, chatbots and videos, explanations, and thought about some other concepts. The framework, another view on it is that a stakeholder usually formulates resilience requirements, that's our vision, in natural language. And therefore we use this, or make heavy use of this ATEM approach from the Software Engineering Institute. So ATEM stands for Architecture, Trade-off, and Analysis Method. Then to bridge the gap to the formal methods, for example, using probabilistic CTL and also MTL, matrix temporal logic, we make use of automatic transformations. So there's a very nice tool called probabilistic specification patterns that uses structured English grammar to formulate sentences, and then there are well-defined transformations to temporal logic. From these specifications, we conduct chaos experiments. We can obtain the requirements, and then we basically at runtime can compare the assumed requirements, the resilience specification with monitoring data, and then can go back and forth via chaos experiments and also simulation-based evaluation. Finally, the stakeholder gets some visualization and interaction. Summary of our approaches. We started, or in the meantime, we did some expert surveys with industry practitioners on how transient behavior is addressed in practice. So do practitioners actually specify transient behavior? How do they evaluate? What are shortcomings with tools and so on? And this is something I will exclude from this presentation today, but Samuel, who I saw is also in this call, was presenting in the parallel workshop in WASP-C earlier today. I will focus on our approaches for scenario-based resilience engineering. And with scenario-based, we always refer to the scenario-based approach from ATEM. I will go a bit more into details here. We combine this with risk analysis methods that are well known from safety engineering. So if you design an aircraft, for example, or a space shuttle, whatever, you need to be very thorough in analyzing or formally specifying the risks of the system and the hazards. This is less often done in applications, so business critical systems such as application systems, and we are basically trying to make use of these techniques also from safety engineering. From this, we want to derive scenario-based resilience tests in order to counteract this problem that I mentioned with which resilience test to select first, so which ones to exercise and so on. Then we have a concept, this is work in progress, formalization of transient specification, and then their runtime verification. And we have some tool support using automation, interaction, and visualization. I probably won't be able to talk about an orthogonal line of research that we are conducting on efficient resilience testing, but I will share the slides in Slack after the presentation, and then you can have a look or look at the respective papers. So now scenario-based and risk-based elicitation. And one big work we conducted here was a study together with industry, and where we wanted to find out how well this resilience engineering fits into their existing setting with specifying or eliciting requirements with this ATEM approach. So ATEM, so the main thing we are using from ATEM actually are these so-called ATEM scenarios. ATEM scenarios is a well-known concept from software architecture. We have 6 elements, so usually specified with 6 elements. There's a source of a change or a stimulus, then there's the actual stimulus. So for example, it's the customer of the system. The stimulus could be an increase in the number of transactions, requests to the system, for example. There's an affected artifact of the system, so a certain service, for instance. There's a response, not to be confused with the response of the actual request, but the expected response of the system. So for example, if there's a failure of a component, the expected response of the system would be to recover this component. This is just the response itself is not quantified. This is happening inside the response measure. So for example, for performance-related scenarios, we usually specify things like the response time quantiles. For instance, 99% of the requests should be below 1 second. And another important part of these scenarios is the environment. So for example, is this change happening during a high load situation? Is it during a peak load situation? And these scenarios can also be expressed for different quality attributes. So for example, modifiability of systems. And then this environment would, for example, be during development time or maintenance or test time. But we are focusing here on this aspect of resilience. The goal of this research, together with the company, was to elicit resilience scenarios. So using this template, here we were roughly following the concepts that are also behind the ATEM approach. What you usually do is you gather together experts from the system, including architects, developers, and so on. And then the goal is to analyze the system, whether it is able to support the scenarios that you defined. And this definition of the scenario is also part of the approach. The prerequisite for this is a definition or an understanding of the software architecture. We did not do this as part of the workshop itself, but we did this as some kind of preparative meetings we had where the architects supported us with architectural documents, and then basically we summarized them and discussed them during this one-day workshop. Next step was the hazard analysis. In this case, we conducted a fault tree analysis. I will give an idea about this in one of the next slides. And here the goal was to identify the hazards that the system is exposed to, and what are the risks and how can these hazards happen. For example, how can it happen that people are not able to buy tickets, book tickets, whatever, something that should never happen. And then we decompose this problem based on the system's architecture to find out what are the root causes. This was an interactive workshop, so really without any technologies, just sticky notes on the wall and then discussions with experts. And I should mention that as part of the experts, we also had, we had 2 architects, 1 quality assurance person, and a product owner that has a good understanding of the business goals of the application. And then we came up with 12 resilience scenarios that we are also sharing as part of the paper. I put a reference before. So to get an idea about the fault tree analysis, here we started with top-level hazards, something that should never happen for this very critical system. So this is actually a system that's being used by many, probably thousands of companies in Germany to make their accounting, basically, and to pay their employees. So the worst case scenario, one of the worst case scenarios is that users' paycheck cannot be calculated a couple of days before the end of the month. And this is very critical for this company because then the connected companies will ask for lots of money, and also there are legal consequences behind it. So then the architects were thinking, how could this happen? For example, the calculation cannot be executed, or the data cannot be captured, or there's an incorrect calculation. And such a fault tree is decomposed using OR and basic event, or OR and end events. In this case, we only had OR. So how can it happen that a calculation cannot be executed, a service does not answer, or service answer do include technical errors? And finally, you get to so-called basic events, which is the root cause of all problems. So for example, a database is full, and then this basically propagates through the system. And we did this. This is just an excerpt of it. So the idea was that now, if you want to get a resilience test out of it, you could use these basic events to inject problems into the system. And once you had introduced counteracting resilience patterns, you could test whether the patterns work as expected or not. So we came up with 12 scenarios. I think I will skip the details in the interest of time. Now we had this list of scenarios and wanted to conduct corresponding resilience experiments. So the idea was we use an established tool, which is the chaos toolkit, and map our scenarios or the resulting experiments to these experiments. So from these scenario templates, we need, for a chaos experiment, we need a fault load, which means what type of fault to inject. We need a workload, which is just like we do it in the load test. So number of users over time, for example, and their access patterns. And we need to formulate a hypothesis. We could get all this information from the scenarios. The fault load can be taken from the stimulus. The workload can also be taken from the stimulus and from the environment. So you can think about a stimulus being a peak workload situation, for example, or you define it as part of the environment where you say we are in a low load situation. Then the response measure goes into the hypothesis, so what we expect, how the system would react, and also goes into the steady state metrics. Now we used established tools. So for the fault injection, we use Chaos Toolkit, and for the workload generation, we used Limbo, which is a tool developed by the University of Würzburg. One example of a scenario-based workload. So we would instruct Chaos Toolkit to shut down the service payslip service at a certain point in time. We define a constant workload of 20 requests per second. Of course, we could also define a time varying workload. And we define that the response time should be below 1 second in 99% of the cases. And for example, one hypothesis could be that the system response time is not affected at all from this fault injection. In this case, again, in the case study, the company, we didn't run it in the first place on the production system or on the real, in a testing environment, but we received a simplified version of the system. They make use of Cloud Foundry, and then we had a setup with the hypothesis validator that we developed, the existing load generator, Chaos Toolkit, and so on, and then we came up with the results that we were expecting. To show you some results, I will again not go into the details, but we see usually in this resilience experiment, we see these kinds of plots. We have a calendar time on the x-axis, we have some kind of a measure, the quality of service measure on the y-axis. And here we can see the pattern I introduced in the very beginning of transient behavior, or the resilience curve. So we see that in the green area, almost until the end, we see that all requests are satisfied. Then in this red area, we start injecting a problem. We can see that the error rate increases, which means the number of successful, or the fraction of successful requests decreases. And then eventually, when the system recovers, we go back to 100% success rate. In addition to this, we have another quality metric here, which is the response time. We can see that during the steady state period, the variability is pretty narrow. Response times are similar. Once we inject the problem, we can see that variability increases and we see a degrading performance. And then finally, in the stage afterwards, we can see that the performance comes back to normal. So this was a setting where we did not have any resilience mechanisms in place. And then what you would do in practice is, for example, you introduce a resilience mechanisms and want to see whether it actually works. We can see this on the right. So we can see that the success rate never decreases and the response times are pretty stable over time. Then scenario-based verification of transient behavior. We see, so I talked about MTL and CTL previously, and this is this notation we see on the bottom, some formal language. What we see on top of it is the structured English language. So the, for example, between property Q and property R, if a problem has occurred, then in response, a certain property holds continually. We can map this to the scenarios that we were identifying in the system. So for example, there's a stimulus and a source of a problem, a stimulus, certain probabilities, artifacts, response measures. and so on. And now the idea is to automatically map these scenarios, or more or less interactively map these scenarios that we identified in the case study to executable and formal experiments, and to cross-check the data that we receive from the experiments. So very similar to our framework before, we have a formal specification, turn this into requirements, we conduct chaos experiments, obtain some monitoring data, and then we use model checking to compare the actual with the expected behavior. Therefore, this is work in progress. So currently a master's student is working on it, and he is extending this established chaos toolkit with the ability to use these temporal logic specifications inside the tool. So this is the like a prototype implementation. We can see that this is this formula represents some kind of temporal logic, and I will exemplify this here. So for example, once we have a response time, or once the response times went below 20 milliseconds, for example, the system will never get back to a response time that is higher than 150 milliseconds. So in a formal way, we can express it like this. It would look like this. So this is the always operator. Eventually, the response time is below 20 milliseconds if the response time, or the response time is never again over 150 milliseconds once the response time was below 20 seconds. So now we can see the tooling infrastructure for this. So some terminal windows with the tooling, for example, Chaos Toolkit and the Limbo driver. Here, the target time means the time we went into the experiment. In the top left window, we specify that after roughly 45 seconds, a failure will be injected into the system. We can see the response times are currently around 7 or 6 milliseconds. Now, Chaos Toolkit will introduce the problem. We see increasing response times, so going over 200, 300 milliseconds, which means that the system, or this hypothesis that I was just formulating, is going to be failing. So now response times go back, but we saw that we were we were exceeding basically the thresholds, and our experiment failed, which means that the actual system behavior does not work the way we expected or we formalized it in the resilience requirement. So now this was about the formal model checking based approach. We have 3 tools that I would like to sketch on interactive and continuous elicitation and specification of resilience requirements. And again, the idea is that we have the software architects, the actual software system, and then there's a feedback loop basically that starts with the elicitation of requirements. So we are assuming that in some scenarios, we don't even have requirements. So we could wait for things to happen in the system and then bring this to the attention of the software architect, and then the software architect could basically formalize or express what would be the expected behavior of the system. In our case, I showed the elicitation using ATAM-based workshops. Then we move on to the specification. I exemplified this. And orthogonal to these workshops, we developed a tool that can use trace data to elicit these requirements. I will briefly overview this in a second. Then we have an editor prototype to specify or to work with these scenario specifications. We move over to the verification I talked about, analysis and learning. We have another tool called Translis that was presented in a previous conference. So first of all, Resirio, and this is an example of a tool, as I said, that combines architectural information. So particularly, we are using trace data from the system to learn which components are in the system, how the systems are interacting. So just like the example that I was previously showing for the circuit breaker. So we automatically So Alex was talking about model extraction in his presentation. So this is basically an extraction of the architectural model of the system. And now we leverage a technique from safety engineering that is called ChezOps. That is a graph-based method where you look at relationships between components and ask what happens, for example, if this this relationship between this component goes away, or that requests are too slow, things like this. And using this, you try to identify risks in the system, and we want to move them into scenarios. For the architecture extraction, currently this tool is using Zipkin and Jaeger, so pretty established open source tools for tracing. For the analysis, I mentioned that we use ChezOps, and then we also integrated a chatbot into this approach so that users can also interact using conversations. And we saw that particularly during these conversations, they were using quick replies. You know this maybe when you interact with Amazon support, when you have some complaints about products, then you can either write something or you get some pop-ups that you can just click, and basically it's a wizard-based approach. As part of the conversation, we build up these scenarios that we learned about. So for example, first of all, the chatbot tries to find out what is the stimulus of this ATOM scenario, what is the source, what's the artifact, what's the environment, and so on. And this is basically what we did in this interactive workshop. But now the hypothesis is that if we have the architecture already automatically extracted, we can do this also using some tool-based approach. We evaluated this approach. The details are in currently in a master's thesis, right? But we already submitted this work to a conference and it's currently under review. So a short demo. Everything starts with uploading a set of traces from the system. Then on the right side, you see the conversation window. On the top left, you see the automatically extracted architectural graph. On the bottom left, you can do some configurations of how the tool interacts. And on the right side, you now see the stepwise definition of the resilient or the ATOM scenarios. So for example, you can select the artifacts directly from the architectural graph. We have, we ask for a stimulus, and these are these quick replies. So these small boxes you can just click, or alternatively, you put in some custom text. So for example, asking about how long is the degradation of the service, when should it come back, and then eventually we have these full ATOM scenarios that we can save and export into a different tool. So for example, using it as the ground truth for our verification that I showed before. Yes, this is the Resirio tool. Then we have an editor for these ATOM scenarios. So you could imagine that now when you left the Resirio tool, you already have a scenario description, which is very basic. So now you want to refine this definition. So you essentially want to come from natural language to formal language. Again, we have this editor chain. So this is an editor with these 6 elements: sources, stimuli, artifacts, and so on. Now, in this case, we are manually editing the information. So you can assume that you basically start from scratch. And the alternative would be you have some predefined scenarios coming, for example, from this previously introduced Resirio tool. You can drag and drop things between the categories of the elements of the ATOM scenarios. And basically, it's an editor for defining and refining the scenarios. Finally, the third tool is Transvis, which serves as the analysis of the observed transient behavior in systems. This was a work that we presented at VisSoft, which is a conference on the intersection between software engineering and software Visualization. Again, we have a chatbot-based approach combined with an architectural view, and there's a visualization. So the core of this approach essentially is this notion of resilience that I introduced in the very beginning. So these so-called resilience triangles, again, we starting with 100% quality of service. We have an initial loss that we also saw in the experiments that I was showing. And then eventually the system comes back. And the goal of this transverse tool is to allow the architects to decide whether the actual transient behavior in the system corresponds to the expected behavior, and also in an incremental step, basically to use the observed data to come up with a good resilience requirement. Again, we conducted an evaluation. Just to mention, because 2 times already we used a chatbot in our work, and I mean, it's not very surprising, but there are people who like chatbots and there are some people who dislike chatbots. So this work was actually before the Resirio work that I was presenting. And in Resirio, we introduced these quick replies, and they were very well accepted, but we made the experience that users usually don't want to put in natural text into these conversations. So, but on a domain level, let's say, the results were pretty encouraging. So the users were able to provide correct specifications and comprehension tasks or to solve them. So in this context, we usually give, or the way we evaluate these kinds of works is that we use a set of experts, give them a system they do already know or they don't know, show them a data set, and then they have to solve some task with our tooling. And the result was that the method was pretty helpful and the visualizations were straightforward. So again, you see an architectural graph that was automatically extracted from system traces. We will see the transient behavior of a service. So here everything is fine. We see a degradation. The system quality of service goes down and comes back. Now we want to add a specification. We can put some kind of characteristics to it. What should be the initial loss? So now what you see already is the actual behavior of the system. And now on top, we want to provide a specification of what should actually have happened. So for example, we can see that the architect or whatever stakeholder we are looking at wants the system to be back in a 100% state much earlier, and the initial loss should be less or lower. There's another plot that accumulates the loss that we observed during the transient behavior, including a specification. And finally, I think that's about it. Exactly, and there's this transient behavior bot that can assist in specifying the loss of resilience and the specifications. So as I said, I could present something on efficient resilience engineering. I think I will just tease the work we are doing here and then move on to the conclusion of the presentation. So the hypothesis when starting this work on efficient resilience engineering was that the current resilience engineering or benchmarking practices are inefficient, which means that we know of these chaos tools, for example, from Amazon, and what they do is they randomly crash components in the system. So without leveraging architectural knowledge, what we do in our works usually is that we automatically learn about the architectural knowledge, and based on this knowledge, we decide what are the most promising areas to analyze. For example, for where to inject problems. So this is the first characteristic of the approach. We consider software architectural knowledge to generate experiments. So for example, we see that in one part of the system, there's a call between services without a circuit breaker. So our assumption is that if something goes wrong with this downstream service, this will lead to cascading failures, and we could design corresponding experiments for this. Another source of inefficiency is that, I talked about it, these experiments are usually costly. You need to spin up a lot of infrastructure power to conduct these experiments. They take a long time. So we use simulation in addition to using real experiments, where we are able to automatically extract architectural models, but then we use a simulator to simulate the way the system would be behaving, and we leverage the knowledge between anti-patterns and patterns and fault injections. So in the very beginning, and you see a pictogram of this, I showed the taxonomy introduced by Michael Nygaard, and our idea was that if you can identify several or some weaknesses in the architecture, this is an anti-pattern. From the taxonomy, we know what is a corresponding pattern and vice versa, and we can decide what fault injections we can introduce. I'm stopping here with the framework, so I'm just sketching the framework. I talked a lot about extraction of architectural information. Again, we have it here. We have the real system. We extract architectural information using usually dynamic analysis, which means monitoring. We come up with an architectural knowledge, and then we have we call it Orca's decision engine, or the magic, that basically decides based on the architectural knowledge and experiments that have already been executed, what experiments to run. Therefore, it generates a specification of workload, a specification of the fault load, executes it on a real system, and then there's a feedback loop basically of the results. And I mentioned that we are combining real experiments, so load and injection-based experiments with the real system or test version of the system, and simulations, so it works the same way. We generate a workload, we generate a fault load. In this case, it's not running against the actual system, but against the simulation model. And again, we feed the data back to the decision engine to think about the next scenario. I will stop here. I have some additional slides, but I will share them on the chat and wrap up. So what I talked about, I started with the motivation of transient behavior and chaos engineering, and then I showed our framework, how we are trying to improve the situation, starting from natural language over formal language, specification of requirements, conducting chaos experiments, collecting runtime data to decide whether the system fulfills or does not fulfill these resilience requirements, and then in the end, supporting the stakeholders to decide whether the system does what it should do. And there, again, you will find some references to our work, and I'm concluding my presentation and looking forward to questions. Thank you.
I put a couple of questions in Slack. So first question, you mentioned using tracing tool for architecture extraction. Could you please elaborate a little bit? And for example, do we need to have an implementation to use, instrumentation to use that approach?
Yes, sure. So actually over the last years, I would say 10 years, many tools were introduced to instrument systems. So in the very beginning, it was very hard to collect traces. So trace is basically a sequence of interactions between components. So usually what you trace is when a request enters the system, for example, a servlet in a web-based application, then you can trace the call to the backend services up to the database. And if you're familiar with UML sequence diagram, essentially a tray or a UML sequence diagram represents one flow through the system. And this is something you can meanwhile easily extract using tools like, for example, we have a research tool that's called Kika. There are some other open source tools. I mentioned Jaeger and Zipkin. There are commercial tools, AppDynamics, Dynatrace, and so on, that give you all this information, and then you can analyze these traces. And architecture extraction, the way we are working with it, usually means which components exist in the system and how do they interact with each other. And this is something you can easily extract from these traces in the system. And of course, in order to do this, because this was part of the question, you need a running system. So otherwise you cannot get the data. Especially you need to do dynamic analysis, which means you need to deploy the system. The system needs to be triggered by some real request, and then you obtain the data and can do the architecture extraction. So we would probably even be able to do it using static analysis, but usually we are using dynamic analysis because we are also interested in the operational profiles. So how many times a component accesses another component. So I'm not sure if this answered the question. I hope.
And another question, nowadays, resilience investigation industry usually associated with chaos engineering tools. You never mention anything like this. How you would map it to what you discuss and how you see the role of these tools?
Yeah, for us, usually these tools, so this is, for us, it's very nice that in the last years, all of these mature tools came out. So I mentioned that we are using Chaos Toolkit. And Chaos Toolkit is essentially a driver to inject problems, for example, into Kubernetes clusters, or we use the Cloud Foundry adapters and so on. So basically the way we use these industry tools is that we use them as kind of the actors. So we in our research decide based on the architectural models which component basically or which service to delay, which architectural entity to crash and so on. And then we generate these fault load specifications. In our case, for example, we use this Chaos Toolkit, which has a YAML-based formalism basically to execute it. So it's similar to our work we did we did similar works also for load testing. And there we, using our approaches, generated, for example, JMeter scripts or Gatling scripts and so on. So again, using established tools that are very well in doing this technical aspects. And here we are focusing on these fault load specifications.
Thank you.
So maybe to add to this, why we are happy, because previously we built our own fault injectors and so on, and very often they have huge limitations and threats to validity when building them, technical issues, and that's why we are very happy that these tools from industry exist.
Any more questions? Feel free to unmute yourself. We still have a couple of more minutes.
Yeah, currently I cannot follow the chat, so I will check afterwards.
Yeah, nothing in Slack so far. Okay, thank you very much.
Thank you for your attention. And I will share the slides also on Slack afterwards.
Yes, please. And for all authors, please share your slides, or for those who has papers, maybe preprint. So, and now it's time for panel discussion. And
Yes, thank you, Andrew, for your interesting presentation. Thanks everyone for being here. So our next session is a special session on panel discussion on performance education and testing. Oh, on performance education and training. Sorry, performance testing is just used too often. So first, I will share my slides. I want to introduce the session and the panelists. Okay. Sorry, just 1 second. Yep. Yep. Can you see my slides? Should be presenter mode. Okay. So in this discussion session, we have 4 panelists. So first, I will introduce the structure of the session. Okay. So basically, this session is organized through 4 topics. So these 4 topics are related to performance education and training. The first topic is learning, how to learn performance engineering. The second is teaching and training from the teacher, from the trainer's perspective. The third one is about resources for performance engineering, learning and teaching. And then the last topic is about looking ahead. What's the future? So we have 1 hour. Each topic will last about 12 minutes. Okay. At first, for each topic, at first I will ask some questions and let each of the panelists to share their opinions. Like each panelist will spend around 2 minutes or something. After that, the audience can ask questions related to that topic to the panelists. At the end of this entire session, so we will leave a few minutes to ask and answer questions as well. So I think we have all the panelists here, right? So I will introduce each of them briefly. Okay, the first panelist is Andrew Bundy. So he's the founder of the Software Engine Performance and Scalability Consulting LLC. His book, Foundations of the Software and System Performance Engineering, was published in 2014. He has served as an adjunct professor of software engineering at the Stevens Institute of Technology since August 2019. He received the Computer Measurement Group's A. Michelson Award in 2016. Dr. Bundy has worked as a senior performance architect at Ferguson Enterprises, as a senior research scientist at Siemens Corporate Technology, and as a principal technical staff member at AT&T Labs and its predecessor, AT&T Bell Labs. He has held senior performance positions at 2 startups. He was a visiting professor at the University of L'Aquila, Italy. In 2016, he served as co-chair of steering committee of the International Conference on Performance Engineering from 2012 to 2021. Okay. Prior to joining AT&T Labs, he was an assistant professor of computer science at the University of California, Santa Barbara. Okay, this is our first panelist. Our second panelist is Leandro Melende. So he's a performance testing advocate with K6 Grafana, helping everyone to run up on their performance practices. He has over 20 years of experience in IT and over 10 years in performance testing practice. So where he served multiple S&P 500 customers all over the USA, Mexico, Canada, Brazil, India, Australia, etc. He's also the author of the popular performance testing blog, Sino Performo, where he creates a diverse set of learning materials for performance testers and engineers. He's an international public speaker, participating in multiple conferences, events, and webinars, with keynotes, workshops, and multiple talks on his belt. And last, he's also the author of the new book, The Hitchhiker's Guide to Load Testing Projects. It's a fun walkthrough that will guide you through the phases of or levels of an IT load testing project. So our third panelist is Alexander Podelko. He's also a co-chair of this workshop. He's a staff performance engineer at MongoDB, responsible for performance testing and optimization of the MongoDB server. He has specialized in performance since 1997, working on different performance-related roles for Oracle, Hyper-V, Athena, and Intel. Alexandra periodically talks and writes about performance-related topics, advocating testing down zero walls between different groups of performance professionals. He currently serves as director for the Customer Measurement Group, CMG, and Organization of Performance and the Capacity Planning Professionals. Our fourth panelist is Professor Wei Zhang. He's an associate professor and Concordia University research chair in ultra-large-scale systems in the Department of Computer Science and Software Engineering. His research interests include big data software engineering for large-scale systems, software log mining, empirical software engineering, and software performance engineering. His work has won premier awards such as SIGSOFT Distinguished Paper Award and Best Paper Award. His earlier tools and techniques developed by him are already integrated into the products used by millions of users worldwide. Okay. So these are our four panelists. So welcome, everyone. So next, we will go to our first topic. So if you look right of the slide, this is a survey by Zipia. Basically, this survey shows what are technical skills required for a performance engineer. So our first topic is related to this result. Okay, in this survey, it shows test scripts, Java, Linux, performance issues, performance analysis, CPU, JMeter, and other skills are the top required skills for a performance engineer. If we want to become a performance engineer, so if we want to learn about performance engineering, so what should we do? Specifically in this topic, we have 3 questions for the panelists to share your opinions. The first one is, how do you learn performance engineering, performance testing, benchmarking? What are skills required to be a perfect performance engineer from your perspective? Last, what are your suggestions for learner and trainees? Okay, so we will start from our first panelist, Andrew.
Okay, thank you for the kind introduction. I'm somewhat perplexed by this pie chart, actually, because test scripting is only a small part of performance engineering. I would ask, what are the skills required to be a performance engineer at various stages of the software lifecycle? So I think it's important to understand what the performance requirements are going to be of the system and how those are going to be linked to business and engineering needs of the system, and how they're also going to be linked to the constraints that are imposed by the system and by the various pieces with which the system has to interact. So definitely test scripting is a valuable skill set. I think performance analysis is probably harder to grasp intellectually than test scripting. Because you need to have an understanding of the analysis in order to structure your tests in a way that's going to inform you about how the system is going to behave. I think having a collection of skills is going to be important. I would say the technology is always changing, so it's important to understand what operating system you're going to be using. JMeter at Linux is less important than understanding the principles of operating systems and how they're evolving. And JMeter is part of test scripting. It's helpful to know that, but if you're going to be doing performance engineering at a really high level, and understanding what the impacts of the system are going to be overall, both before the system is built and afterwards, then I think analysis and an understanding of the operating environments, the others, I'm not sure what's listed under the other skills, but those are very important. And also being able to communicate data very well is extremely important. I don't see any mention of data communication and data analysis here. I think those are very valuable skills as well, unless you, it might be there hidden in performance analysis, but I don't see it there explicitly. And my suggestions for learners and trainees would be focus on the bit that you're working on at the moment, but understand the context in which it fits. So if you're doing performance testing, for example, and you're writing the scripts, understand whether the scripts are a realistic representation of the workload that you're testing, and whether the test is going to be structured in a way that's going to help you uncover the root causes of performance problems.
Thank you, Andrew, for your interesting thought. So the next one, I think, goes to Leandro. Can you share your opinion about this topic?
Sure, Hank, thank you very much. It's a very interesting point to notice that the test scripts is the first place, very similar to what Andre is saying. Although I kind of understand it, looking at the industry and fomented a little bit by this confusion, or many like to use performance testing and load testing interchangeably. And this is a something I feel at times has been propelled by the tool vendors, where many tasks around performance testing are start scripting and load testing, slamming the systems. And it's still somewhat adequate, or it's true in the industry. Most of the entry jobs that you will find around performance testing is as a scripter. And it's the very first step. I think it's, even as I don't like it that much, is valid. The first step that many should start learning or gather when they are trying to get into this performance world is scripting. You will need lots of understanding, protocol, how the communication happens, some learning around that. I would suggest to try the low-level tools for this, not focus so much on the graphical interfaces, drag and drops. Even with those, you need to understand some key concepts behind. But again, I do agree that that's part of the skills, at least to be employed, right? This is important for most of us. But to truly be and understand a performance engineer in practice and be, I disagree a little bit with being a perfect performance engineer. You cannot be perfect. You can try to be great and keep it pushing us. Very well said. It keeps evolving. We will see things changing. But it's a trade where I think it applies the most, this full stack engineer. You need to understand lots of pieces, lots of components, databases, networks, infrastructure, CPUs, development, code, all that is super important. So I would suggest get a general knowledge around, and suggestions as well to stay up to date or to be the best possible performance engineer once you're good at scripting, because I feel it's a trade that it's kind of on its way out. We will always be scripting, but not as much as we used to. And even nowadays, I keep seeing in the industry that this is a downtrend, scripting. And I would suggest focus on observability, understand the system, understand the analysis, understand how to detect these bottlenecks, not so much on triggering them, because all the switch left and switch right, practices are encouraging us to be more analytical, to understand the infrastructure of the system, how to detect, how to alert, and be ready for those. It's more performance testing, not load testing only. We need to know the performance of the system, and this is going to become a big trend if it hasn't already.
Thank you, Leandro. So I want to remind everyone, if you have any questions, please post your questions on Slack. So we'll take the questions at the end of each topic. Okay. So our next panelist, Alex, Can you share your opinion?
Yeah. Several points. First, about learning. Usually it is very interesting. There is no standard path into performance testing or engineering. Everybody coming from different parts, and there is no standard way of education. And usually it is kind of on job or somehow getting through mentoring. No real, very few programs in performance in general, and especially in performance testing. Next, it is changing drastically. As I mentioned, with agile development, everything is changing. Before it was pretty established process when you need to test system before you go in production to use load testing tools. So that survey results which we see here, I think reflect that traditional legacy approach. That was how it was 10 years ago, and with all discussion around mostly load testing tools, and everybody said that, yeah, you need to understand performance in general, performance analysis. And now it's changing because with agile development, you start to get involved earlier, and you definitely need to do tests differently and understand it much deeper level. And I don't think that it is settled already. So that is something that we see right now, developing right now. Different companies approach it somewhat differently, but definitely it's changing. Scripting kind of stopped to be the main topic. And most advanced systems that I know about or read about use some kind of proprietary load generation. So that is why I thought that maybe vendors are a little behind with current trends, or maybe new deeper level of performance engineering and testing require more specialization. So generic tools doesn't fit that point. That is open question. It would be interesting to see. Another point, I was from education, I was involved, I guess, in couple of things. First, I for a long time participated in organizing CMG conference where we tried to broad these topics, and now in that workshop, because there is some basics and there is advanced topics, and probably conferences is one good way to get more advanced topics and get some kind of maybe mentoring connection, because it is one of the biggest challenge. It is very broad area. So yeah, you need to have good fundamentals, but everything that you need to do practically, you need a lot of very specific things about that specific technologies, specific hardware architecture, specific performance tools, specific tools for analysis, specific monitoring, instrumentation. And truly speaking, there is no way you know everything well. So that's very important that you have good basics, and you then kind of learn as you go, reach to other people, find the right information to solve these practical questions along the way. Another things I was involved was efforts to do certification, and that again challenge what you want to certify people. Found definitely not kind of specific technology because it is very specific, but it is difficult to certify it foundation without any actual practical things. So it most cases didn't well too far, although at some point I was involved in one certification that was released at STQB performance testing certification, which may be decent enough for entry-level performance testing. Maybe if you haven't seen it, you could check. I don't know what is value to get it, but at least it has an interesting list of what basic knowledge performance tester should have.
Okay, thank you, Alex. Our next panelist, Asian, can you share your opinion on this topic?
Okay, so thanks for the introduction. Right, so I just want to first comment on the chart. I think that the chart is very interesting. So the biggest part that astonished me is the other skills takes more than half of the chart, right? So basically that means the need of skills that are really diverse for performance engineering. So that actually now if I really think about it, I think that's basically what the job is, right? I think when you talk about performance engineering, you talk to different people. Actually, that means different things to different people, right? A lot of people, if you say performance engineer, mostly they will think they are performance tester, right? Or a performance analyst, right? There could be other performance engineers. For example, in the design level, right? So they draw performance models, right? That's completely different from doing performance testing, performance benchmarking. That's completely two different jobs, right? But they will be called performance engineers. Right? So now, if really, I'm even thinking like whether it makes sense, right, to say they are actually the same job or they are the same role in the development. So also, I think the other panelists, so what they mentioned makes a lot of sense. So one of the ideas is people always say this, right? So performance is, I think, it's less and less to be in like one step of the development or in a life cycle of the product, right? So more and more, I think they kind of integrate it into every step in building your software, right? So especially in this agile and DevOps trend, right? So basically, you need to know everything. I think that's the challenge, right? I think from an academia point of view, for example, in Concordia, there's no performance engineering course, right? And I don't see a lot of universities offer a specific topic of course in performance engineering, right? So you kind of need to teach them in different steps or integrate into different courses, right? So I think that's actually not only give a big challenge to the educators, also for the students, right? So they never really get at the bigger picture of what's really performance engineering is, or what is overall this performance is for software. So they have to pick up the pieces from different courses and from different sources as well. So I think, yeah, I think that's my overall impression of this.
Okay, thank you for all the panelists on this interesting topic. So we have, let's take some questions from the audience. The first question from Tori Williamson. So his question is to all the panelists. So one issue identified by academics is in system areas, for example, OS architecture, networks, security, is that industry eats the seed corn. That is, they consume our student trainings, often before they are ready. And none of them stay in academia to train the next generation. Is this same problem happening in the performance community?
Well, it's something that's in academia, college and universities is you don't see a QA career or a course even. I mean, I have not seen yet, or I'm aware, probably I'm a bit out of it, but I don't think there's that much still. And it's sad. I mean, it's an area that will start to get a little bit more attention, will start to grow, and it definitely should be added to the main topics that are to be taught in academia. It's similar to pairing up, you learn how to do a round robin or a ordering a list. Well, also make it efficient, add some of those elements so that people that come out of college are already at least aware of that importance, which is instinctive, but there's not that much. And that one, to stay up to date and learn the newest and best practices, I do agree with Alex. Conferences, meetups, getting near to some gurus or heavy skiers would be the best, because also it's an area so big, and as Will, I think, agrees, you need to know so much of so many other things that it's hard to pin it down, and it's not a silver bullet always the same for everything. It's very contextual. So there are several challenges there.
Thank you for the for answering the question. So there's another I think it's more discussion from David Daly. He's saying that you see a difference between performance technician and performance engineer, but people go to label themselves in their resumes. So, and I think there are a lot of performance technicians out there driving this chart. So is for Yan, Wei, do you have any thought about this one?
No, I 100% agree. I think that there's a fundamental difference between performance optimization and performance engineering. Yeah, like in the beginning, I mean, like in the beginning, like Jen, like in the book, I think everyone knows that book. So it says performance engineering is an art, right? But now when we talk about performance engineering, basically that means we don't want to do it like an art. We want to do it in the engineering discipline, right? So I think there's a fundamental difference between that.
Yes, Andrew.
Yeah, I'd like to speak to both questions.
Yeah.
First of all, speaking to Carrie's point about seed corn, one of the problems, at least in North America, is that performance engineering courses are not really attractive. It's very difficult to get people to take them because they find the mathematics rather daunting, or because they feel that the field isn't sexy enough the way computer graphics was in the 1980s, for example. I wish that Andre Van Horn hadn't just left the conversation, because he could tell us what's happening in Germany. And in Germany, the Netherlands, and Italy, there's far more instruction and performance evaluation, performance modeling, performance engineering than there is here in North America. And there are a few places in Canada that do it too. Some of them will go into academia, some of them will go into industry. I don't think the problem is as big a seed corn problem in the sense of people being taken into industry specifically to do this kind of performance engineering task. My experience in industry has been that there's actually resistance to performance engineering that's somewhat analogous to the kind of problems that we see in academia as well, which is, if we pay attention to performance, we won't deliver the new features on time. There's an analogous focus on features rather than on performance. And in academia, there might be a focus on whatever the latest hot topic is going to be. In the 1980s, it was graphics. In this decade, it's machine learning. And there's always an issue of whether time to teach performance is going to take away from the time that's needed to teach the other stuff, some of which is demanded by industry. So maybe we actually need to create more of a demand in industry. I'd also like to speak to Professor Sheng's point. I'm actually an adjunct professor at Stevens Institute, and my colleague Ye Yang and I have a National Science Foundation grant starting in June, whose subject is how to integrate performance topics into standard software engineering and computer science courses, because they don't receive enough attention there. So this is something that is beginning to be looked at. I'm very pleased that the NSF thought this needed attention. And I didn't answer David Daly's question about technicians versus engineers. My understanding is that an engineer is someone who is going to be going in from the very beginning and be involved with construction and testing and so on. Whereas a technician is someone who might be changing configurations and so on. Whether the configurations are changed the right way is another matter. David, is that what you meant?
Oh, I just meant along the lines that an engineer goes in and deals with hard problems and takes some theory to it and probably some design into it, whatever stage they engage into it. Where a technician takes a list of things to do from somebody else and executes on them. And when, in the past, when I've tried to hire people for my team, I get a lot of people who are applying who are fit that category, and a lot less who are doing stuff in practice, who are doing what I would consider real engineering. I know I'm throwing a little bit of gasoline here, but that was sort of how I experienced it.
I think that reflects the recruitment situation as well, that companies other than yours that might be less forward-looking. There's a lot of emphasis on testers per se, rather than on people who are actually going to use the test results to do some engineering, which is and that's somewhat ironic, because usually the performance requirements haven't been written in the first place.
I think we should move to the next topic, because we are taking like half of the time already. So fortunately, our next topic is very similar to our current topic. Maybe some of the opinions can be like discussed there. Okay. Our second topic is more towards the other side, the teachers trainer, about teaching and training. So this is so if you see, there's a table, and this is from the presentation paper last year by Ms. Connie Smith. So basically, this table summarizes some areas, some topics that may be included in performance education. This includes software development, for sure. This is related to performance. Second is performance modeling and evaluation. Third one is benchmarking, evaluation. Last one is performance improvement. What about anti-Pythons, tuning? So I think this topic is very related to our previous topic. So maybe this time we don't go to like a one by one. So we just ask. So if you have any point you want to share, just please go ahead, and then we take some. If you have any questions, please post your question on Slack, and we'll take it to the panelists. Okay. Basically, the questions we have. So, what are your best practice in performance education training? What topics should be covered? What are your suggestions for educators and trainees? So please go ahead. We don't do one by one. We just just share. Feel free to share your opinion. Please go ahead, Leandro.
You say Andre?
Oh,
Leandro.
Sorry. No. Leandro. So how to actually pronounce your name? Can you repeat?
Leandro.
Leandro. Okay. Yeah. Thank you.
I mean, and that's kind of personal to me. What is the departure point? And that's general for training and education. You gotta make it entertaining, the rapport, and make it the people be involved. Very much like Andrew was mentioning earlier, it seemed as boring, not attractive. We gotta make it sexy in a way. Appealing to people, to say, okay, even if I didn't want it, I ended up learning some of performance testing from this content presented in a way that is engaging. I mean, this is not so much related on performance per se. Training in general, I think, has to be engaging, mostly. And I think that would be the main recommendation that I would do or give, and it's something that I personally try to do a lot to make it palatable. There are times where, yeah, you may be in a a set of mathematicians that are with you, and they don't want to hear about, but in my example, tacos and puppies and getting those analogies. They want, hey, I want hard numbers. I came for the science. But there are some others where, and especially for training, for starting, for people that are not that familiar with some of the topics that we use, terms like throughput and hits per second just out of there. And so many times I have faced situations where the audience, even if they have been doing performance testing or automations or things like that for a while, they don't know or fully understand. So I think that would be my main recommendation, make it engaging. And I think the topics that we said, that 50% of the graph, that is a lot. We need to learn a lot about all these. I think the principles, good analysis, and understand how to measure and gather those metrics about performance. I think those are the cores. Scripting maybe in third spot, but all the other ones are really, really going to be important for the future.
Thank you, Leandro. Like any other sharing, any thought?
Yes, I think this is one of the most interdisciplinary subjects you could possibly imagine. I came from a math and stat background, and then I did training in computer science after being exposed to performance. And I've used just about every aspect of every discipline that I've ever studied in performance one way or another. I think it's partly a question of knowing your audience and what they need to know now. In the Passover Haggadah, which is going to be read on Friday and Saturday in Jewish households, at the end, they talk about how you explain going through this ritual to children with different levels of intelligence and different levels of curiosity. And I think there's a very strong analogy here between that and understanding what's going to appeal. At Stevens, I've taught functional testing, and I've also taught a general software engineering survey course. In the latter course, I go through and I try and inject performance topics that appeal to people's feelings about how the workflow is going through the system and where the bottlenecks are likely to be and where the response time requirements are going to be. In the functional testing course, we've introduced a few hours of performance testing instruction in which we talk to them about using something like JMeter in order to drive loads, but we also have to spend a little bit of time on the basic laws in order for them to understand how to interpret the test results in the first place. And we have them do basic measurement on their own laptops of the way YouTube videos are behaving with different kinds of activities going on, so they can get a feel for how resource consumption is going on. So I think it really has to be tailored to what you're talking about at the moment, and also understanding what the need is at the moment, as well as going through basic principles. This morning, Vittorio said that when he teaches his QA course, when he talks about operational analysis and the basic queuing laws, half the class is bored, but they still need to know it. And they will eventually use it.
Actually, it is an interesting point because, again, all these university performance engineering classes were usually very math heavy. So usually 3/4 was about querying theory, which definitely good to know, at least about kind of basics. I am not sure that advanced math is so helpful for even for people who work in performance engineering, but looks like actually reality changed a little with now more stress going on horizontal scalability and some other stuff that in some cases we even don't need a queuing theory to make some kind of simple model about performance. And especially maybe undergraduate studies. Maybe we need to do some kind of simpler, more practical stuff that people could use. Yeah, I mean, idea to add that information along with standard classes make perfect sense, because it is maybe difficult even to take all these pieces together in a separate class, because it all interrelated. When you talk about architecture, you need to talk about how architecture could impact performance. And another notice, maybe to previous topic about technician, yeah, it looks like there was a lot of people who usually referred not to technician but performance tester, which concentrated literally on running tests and scripting. And yes, looks like that skills are less popular nowadays, and maybe you need to learn much more now to progress in that field. But from another side, I also noticed trend kind of downgrading testing aspect, especially in academia, because testing aspect doesn't mean scripting. The way you design tests, how many tests it should be, what you should select for testing, when you need to run it, why you need it. All these aspects actually not so trivial, and usually almost completely absent in academia area.
Mm-hmm. Yeah, thank you, Alex. I think anyone else have anything to share? Let me check. Yeah, there's no question. Just a reminder, if you have any questions, you can always post your questions while the discussion is going on. Okay. So we have two questions from Slack. So I would ask. The first one is from Marius. I don't see workload modeling on the teaching and training slides. Workload modeling. So basically, yeah, it's missing here. So do you think we should include it here? I think it's more like maybe. Sorry.
It is part of benchmarking and evaluation, because I think benchmarking on this slide means all testing efforts.
Yeah. Also, like maybe part of the performance modeling in general, I think. So there are also some comments. I will just read it out. So from Curry Williamson, performance people need more than one tool in their toolbox and need to know when to use each tool. Second one is performance analysis are broadly applicable across many domains. Connecting theory and practice is important. Students need real case studies. Yeah, totally agree. Yeah. So I think so we can. So we are like we're running slow. Let's move to the next topic. Okay, so next topic is also very interesting. It's about resources. So here there are many resources here. Just I list some of them that like there are classic books or recent books. For example, the book Performance Solutions by Ms. Connie Smith. It's a classic book, 2001 around, under the book of Foundations of Software and System Performance Engineering by Andre Bundy, and I think it's 2014, right, published. And the two recent books, Systems Benchmarking by Samuel Konev and his colleagues, and also a book on the Hitchhiking Guide to Load Testing Process, so which Leandro also mentioned earlier today. So I think so these are these books, and also we see blogs, we see websites. So there are many resources. But if we're teaching or like we're training students or like new learners, so what are best resources do you think we could use? What things are missing? What are the biggest challenges? So I just maybe if you have any thought, just share your opinion. Thank you. Yeah, Leandro, please.
Well, again, this goes a little bit on depending on who is the pupil or who is learning, because there are people that like to read a lot and would absorb the information. There are others that would like a workshop while they are doing the things is the best way for them. And some others just like to watch videos or watch content happening to understand. I think a big advantage right now is that we are getting many different channels how we can start to learn, and many are generating content around it, not only books, which have always been the traditional mean to learn and gather some insights, but as well, one hand, how people learn, all the other options. We have things like Udemy, we have YouTube, which I think we're streaming to or will be online. So many sources. I think everyone should choose according to what is how they learn the best, what fits the best for them. And because this draws a line very similar to what the roles and positions in performance testing, coupled with HR not knowing what is specifically what someone has to do. Here as well, the information is so big, so many topics, so many, I would say performance testing has so many specializations that we could fall into, but at the same time, we need to understand a little bit of all of them and each of them. So in general, there are many people pushing content on blogs, books, videos, trainings, workshops, and probably maybe even others soon. I don't know, the metaverse. I have seen some people asking, how can I start teaching there? How can I start making it more interactive? So I would say first, as the learner, people looking for information, ask yourself, what is the best way in which you learn? What will be more fruitful for you? Some like to read blogs, some others like to watch videos and see how someone is clicking on the tool or drag and dropping in JMeter or putting the URLs. Others have to do it until then they will understand it. So there are so many options. I would say go nuts with them. Make sure that you pick the ones that are best for you. There's so much. Have fun, I would say.
Yes, thank you, Leandro. So any other sharing? Yeah, please.
Okay, I'll go first. Sorry, Andre. So from an educator's point of view, right? So I know there are many good books. I think a lot of the comments I'm looking at the Slack as well. I think there are many good books, but from an educator, what I really feel is needed is the subjects that we can use to teach the students, right? So performance, I think performance is a little bit different from other aspects in software engineering. Basically, you need a product. Not only you need a product, you need a running product to do performance, right? So that's kind of like the last step you can do, right? So in order to teach students, you need to reach to the last step, that's to do something, right? That's a big overhead from educator, right? So you need the system. Not only you need a system, a lot of the things we teach only makes sense or makes more sense when the system is complex or your environment is complex, right? A more like an industrial setting, right? So we can teach with toys, but students sometimes they just don't get it. Like they don't, with the toy example or a toy setting, the students won't see the need or what's the beauty of this, right? I think from an educator's point of view, I think what is missing is like something that can be used for education, but that's complex enough that students can actually learn and know what's the need of this, right? And something that's actually playable or touchable, right? Yeah, that's my thought.
Wei, are you suggesting that there's a need for project work here so that students can get their hands dirty and actually start applying what they're using in class and come to grips with the complexity and the limits of the simple techniques that they're using? Is that what you have in mind, or is that where one needs to go?
Yeah. Yeah, something more complex. I would give them something simpler to play with, right? Like a website, right? Or like a 3-tier like a database. But I think that's just in reality, like the real life, the industrial systems are way more complex than that, right? So they can do performance model on like a simple website, but they just don't see the challenge and the pain of actually what people will feel in the field, right? But in order to get a complex system for them to play with, that overhead in classrooms or in university trainings are really, really hard.
It's expensive to do, and it's hard to get real examples because when companies are having performance problems, they don't want to talk about it. It affects their competitive edge.
Yeah.
Yeah, maybe I will just quickly share the one related thing, right? So recently, a group of professors from US, so Clarkson University and Commonwealth University, what they do, so not performance, but for software engineering. Basically, they take an open source project, complex open source project, but they build some features and they build some solutions as well to the features as well. So they build like up to 10 software projects with different features. So, and I assign these features to students, and they also provide solutions. I think that maybe that's something we could think of. So to provide some like standard complex projects for performance learning. I have the same concern.
It is an interesting proposition because you got me thinking now that we have some of these containers that learners can just download a container or a few that have like a full stack, as you were saying, Wei. I like that a lot, like having the database tier, something smallish, some code, the solution, the web front end, and to start trying it and even like assemble something on purpose, like, hey, this has a degradation issue here on purpose, detect it. Like the experience of finding it, I think would be awesome for learners to get that hands-on experience and truly find defects. That it sounds like an awesome proposition.
As we are like yeah, thanks. As we are like we have 10 minutes left, or less than 10 minutes, so we will go to the next topic. So there are many good books, several good books mentioned in Slack channel. Thank you very much. We will definitely take a look. And our next topic is about a future, looking ahead, right? So this is from Alexandro, basically in his talk in CMG 2021. This is this is online. So he mentioned what is ahead for performance testing. Basically, performance testing is being replaced by other methods of performance risk mitigation. And also is the responsibility of moving to other areas, such as to developers, to SREs. And also, so the emerging of self-management, self-scaling, auto-scaling systems to make this performance testing maybe less necessary, maybe. So the good thing is, so the system scale is going up. So we need performance, we need to ensure its performance, and the cost of resources becomes significant for large systems, and cost of failure increases, and also the trend of decentralization. So here we can see the things in the future, or like a lot of these different from things in the past. We have different focus probably. So I want to ask your opinion. What are next biggest things in performance engineering, testing, benchmarking? What can the industry or academia do to improve the current status of performance education and training? Then we get some answers from previous discussions. So if you have, so please go ahead. Feel free to share your opinion about this topic. For the audience, if you have any questions, please post on Slack. We will take it from there. Okay, please go ahead, Leandro.
Well, looking ahead, I totally agree. What was used to be the traditional entry point and the main activity for many performance testers, that was the scripting, that's fading out. So many of the tools, so many of the team shifting left, shifting right, is giving us, I think, or my proposition here is that the performance engineers or performance-related people, because I truly think that these roles and responsibilities will start to get blurry between one and each other, but would be more as guidance to the teams where we are working on bringing the experience, which gives us another interesting conundrum to get that experience, but bringing a teaching on the shift-led side to developers, what should be careful for, what should be looking for, and on the right side as well, help to get like, hey, this is not a fixed response time, look for a deviation instead, or things like that. I think that's going to be the biggest shift or change, kind of pun intended, that we are going to be getting. Performance engineers, specialists, or performance people, however you want to call it, the biggest challenge is like understand as much as possible from all the components of the system, which keep getting larger and more complex, more sophisticated, or understand a little bit, like have an insight who to look for, who to recommend, or what to do, and start implementing and giving recommendations to the teams. Because with the new agile teams, you won't be even at times like fixed in that team. You'll be jumping around teams, trying to help them, trying to guide them. It's not cost effective that you are, or time effective as well, that you are sitting there waiting for something to be finished and be given to test and give back, which was at a time our focus. And in the same time, on the right side, checking production, doing tests, checking that it's okay. Everything is going to be spinning so fast that you need to delegate so many of these and just give some guidance, give mentorship, and be kind of the compass in terms of performance around the team. I think that's going to be the crucial thing. And sadly, the biggest part will be understand as much as possible of the system and every performance related shortcoming that you may be able to give advice. That would be mine.
Thank you very much, Leandro. Very interesting. Like, so we need to be like proactive, right? Okay. Next, so anyone else want to share your opinion about this topic? Or if you have any questions that you want to raise, you can post it on Slack.
So you use my slide. So he is my opinion about trend. From another, yeah, it looks like we have turning point to that new kind of performance engineering, and probably education and training get much more behind even that how it was before, and it wasn't too good before too, because big part, I think earlier, first it was load testing tool vendor education. So I know at least quite a few education went through that when people, maybe not in relative number, but it still was a way to educate people, maybe too heavy on tool itself, but they still provide some important basics, and looks like it also somehow fading away. Maybe, I don't know, maybe because companies just not sending people to training anymore. Looks like there is kind of the decrease in education, and big companies usually had on-site training for their employee, and also it looks like somehow going away to maybe some informal discussion. So almost everything now to learning on the job. And I think somebody should pick up it and fill the gap and need into performance education.
And keep sending people to conferences, because that is a very enlightening. You will surround yourself of knowledgeable people, getting new trends, new things. I think that also is a very good practice for people trying to learn and get better and get the newest or best ideas. I think that also is priceless.
Yeah, and actually conferences not so popular as they were before. So it looks like they get smaller, and organizers have more and more problems, losing money with it. And of course, COVID didn't help it either.
Okay, yeah, thanks. Very interesting discussion. Any other thoughts? So I think we are here almost time. So we will go to our last. Basically, this is not a new topic. Basically, we have 4 topics here discussed. So what is your final thought that you think missed? You didn't had a chance to share, so there's a final opportunity to share with us. And if you have any question, there's a final opportunity to ask your question. I think there's a first. I'll start with a question from slide. Okay, it's from Yusuf Meyrov. So to the problem and not to the problems and not to the tools, Pythons and anti-Pythons seem to be more important for performance engineers. What do you think? Basically, the code, the Pythons and anti-Pythons in the code may be more important to the tools. Yeah, please go ahead, Andrew. Yeah.
I think we want to get, Joseph is touching on an interesting point, which is that we want to prevent the performance problems from happening in the first place by being attentive to the design and how things are going to fit together. And recognizing the patterns and anti-patterns is one way to do that.
And I would add around that, don't focus so much on a tool or learn the concept. I always give this example. If you understand how to use a clutch, a gear, and the shift, you can drive a truck, you can drive an old Volkswagen. Understand the concept behind all the patterns that you have to follow for performance. And then most probably you'll be able to pick up any tool just knowing what you have to look for.
Okay, thank you everyone, and thank you for the interest in sharing, and thank you for your questions and all the resources that we have on Slack. So we hope we can continue this discussion in the channel, Slack channel, and thank you again for all the panelists. And let's go to our next session. Thank you.
Thank you for having us.
Thank you. Pleasure. Have a good day, everyone.
Have a good one.
Yeah. And now we have final part of our workshop with 3 presentation, 20-minute slots. So next one from Devon Hockey and Carrie Williamson from University of Calgary, benchmarking runtime scripting performance in WebAssembly. So go ahead.
Hello, can everybody hear me?
Yes.
All right. So just going to go over our project, benchmarking runtime scripting performance in WASMR. I said that my name is Devon Hockley, student at the University of Calgary. I did this project in collaboration with Carrie Williamson, who's a professor at the University of Calgary. So we wanted to demonstrate that WASMR can be used to create an embedded scripting environment. So think something like Lua or Python that you'd embed in your program to allow users to extend it at runtime using, except instead of being bound to like Lua or whatever your other language is, allow them to use a variety of different languages. To do this, we created a set of micro benchmarks to measure the performance of different techniques of talking to this WebAssembly code. And based on that, we created a larger macro benchmark to use as a more realistic application or use case. So first, what is WebAssembly? It's a standard created by the W3C and Bytecode Alliance, designed to provide a high performance virtual machine in the web browser that can run all kinds of different languages and is sandboxed so that it can't do anything malicious. And it can interoperate with the JavaScript environment in order to talk to the browser, but it itself isn't bound to like the concept of the web DOM or anything like that. So it needs to use JavaScript to talk to that as like a bridge. Under the hood, how this works is it's a rather simple stack machine. There's a WebAssembly text format in the corner. And it's fairly simple. Provides only functions and modules, and it's very basic types, just 32 and 64-bit integers and 32 and 64-bit floats. These source codes are, or source code of your written language like Rust or C or C++ or whatever, are compiled to WebAssembly bytecode, or WebAssembly text format is compiled to WebAssembly bytecode, which is then downloaded with your application and interpreted or just-in-time compiled by a local WASM virtual machine to your native assembly code. There's a few existing WASM implementations outside of the browser, in addition to those in your Chrome and Firefox or whatever. Two that we looked at were WASM-Time, which is a reference implementation created by the Bytecode Alliance. And the one we used for our actual project was WASMer, which is a separate implementation created by the company of the same name. WASM-Time only supports one JIT backend, but WASMer supported multiple, so we were able to evaluate the performance difference between those different just-in-time compile backends. As for applications of WebAssembly outside the browser, there's two here that kind of inspired the benchmark, I suppose. First is Lunatic, which is a high concurrency Erlang / Beam virtual machine alternative. You run it on top of either WASM-Time or WASMer, and it prefers many small scripts. So example I wrote here is using it as a web browser, creating one virtual process per incoming HTTP request. So each individual WebAssembly invocation is really small. And then the other example we have here is Valoran, which is a open source 3D game, like an RPG. It uses WebAssembly to allow users to extend and add to the game without recompiling code into it using a event-driven architecture. So you'd write like on-click handlers or on-hit handlers or whatever kind of event you want to listen to, and those would be triggered as those events come in. So again, lots of very small invocations rather than long-running functions. There are some previous benchmarking attempts. The one here is a paper from the University of Massachusetts that found a 2.5 times performance penalty running the spec benchmark in WebAssembly. They tested this by compiling it to run in the browser. But this was focused on a long-running program, not a series of many short functions. And it also, as far as I can tell, only benchmarked WebAssembly implementations within the browser, not out-of-browser ones like WASMer or WASM-Time. So that's basically where our benchmark comes in, is we want to benchmark the WASM-Time WASMer ones that run outside the browser. But we also want to benchmark implementations that use lots of short-lived function calls for event-driven systems and user-scripted systems instead of large complex procedures. So now I'm going to go through our experimental methodology. So we created a series of micro benchmarks. We chose WASMer, and we used Rust for both the benchmarks and the modules for the benchmarks because WASMer itself is written in Rust, so it made that much simpler to operate with. And then by by allowing direct memory management, we were able to be a bit more fine-grained in our methodologies and the different things we tested. And then the modules were written in Rust just because it has a very mature WebAssembly backend. So it made the benchmarks easier to write. We have a lot of experimental factors that we tested. So the main one was we have 3 different ABIs. These are basically different ways of calling from the host environment into WebAssembly. and passing your data across. So we have pair, bin code, and bytemuck for that. We also benchmarked how important caching the references were, and these references that we cached are essentially function pointers to the WebAssembly module, so that we don't have to look up the method we're calling every single call. We also tested some individual characteristics of the different modes. So for example, for the pair ABI, we tested hot loading and preloading the data. It's just two different ways of loading the actual arguments that we're calling. And then we also tested a self-referential struct caching mechanism. This is a special case of the caching that stores the plugin or module as more of a object-oriented pattern where you have a single data structure that has your loaded code and all your function references, similar to how you might want to structure an actual application. And then for bin code and bytemuck, they involve a memory allocation within the WebAssembly sandbox, basically shared memory to pass data back and forth. And bin code and bytemuck, we tested both dynamic and static memory allocation, but bin code doesn't seem to support static allocation because we need to know the memory size of what we're storing at runtime, or at compile time, sorry. So we weren't able to test the static allocation for that in our benchmark. We ran our tests in both debug and release mode for the Rust compiler, which is approximately equal to or the release mode of the Rust compiler is approximately equal to 03 in the GCC or LLVM. And we also ran them against the 3 different just-in-time backends that Wasmer provides. So that's the single pass compiler that was created by the Wasmer, Inc., and which is optimized for fast compile times over optimizing the output. Also tested the LLVM backend, which LLVM full compiler backend supports a whole ton of optimizations, as well as the crane lift compiler, which kind of falls in between the two. It's designed to compile code faster than the LLVM, but doesn't have as many optimizations, so the produced code might not be as fast. I'm going to quickly go over our ABIs. So the pair ABI is very simple. You just pass your arguments directly. Same as calling using a C ABI to call the function essentially. Although by being so simplistic, it's limited to your native WebAssembly types of 32 and 64 bits, integers, and floats. The bin code ABI is a little bit more complicated. Basically, we get a buffer from the WebAssembly module and then copy our data into it. And bin code, or we use the bin code format to do that, which is it's a binary format, kind of like protocol buffer. So it's a serialized binary format. And then we call the method, pass it a point, pass it where we stored that data, and it deserializes it back into a struct and performs the operation. Very similar to this, you have the bytemuck ABI, which works much the same way, but instead of using a binary serialization format, we just write the C struct directly. And then the bytemuck library just helps us with byte alignment. It performs essentially zero transformation of the data itself. Of course, you're limited to things that we can represent with a C struct in that context, and languages that can actually make use of a C struct. Based on the results from the benchmarks we wrote with the previous table of factors, we created a web caching policy simulator using basically the same architecture. We skipped a handful of factors, such as dynamic memory in the case of bytemuck, because they performed just strictly worse. And this web caching policy simulator, we tested a handful of different cache policies. So first in, first out, least recently used, least frequently used, and GD size. And they were selected just to stress the system in different ways with different data structures. So the actual results of our benchmark. The micro benchmarks with the single pass compiler, you can see that the cached variant of all of the other factors performed better than the non-cached one, essentially all the time. Bytemuck and bin code performed similarly, but when bytemuck has the static allocation enabled, then it performs much closer to the pair performance, slightly slower, but not much. Performing much faster than the other more flexible options. Pair performed the best across the board, although as mentioned before, it has limited use cases due to the simplicity of the data that we can pass. For example, no variable length data. Moving on to the crane lift backend, you can see things get somewhat faster. Pair doesn't improve very much. The relative ordering is about the same, but the gap between BiteMuck and BinCode's dynamic implementations closes a fair bit. They get much closer. Code compilation was only slightly slower. The final backend, the LLVM, didn't really seem to have an effect on the performance, most likely because our program, while being a more complicated use case, the scripts are still pretty short and they're just not that complicated. However, compilation speed, when we factored in, made it perform the worst by a fairly large margin. This is the compilation time to take the WebAssembly bytecode and JIT it to native assembly. The other crane lift and single pass, the times only go up by around 50%, but LLVM almost quadruples in the worst case. And again, this is likely because the LLVM runs through many optimizations that don't do much on our code, is the best guess, I guess. So going to the macro benchmark, the hot load versus preload, there's no difference in release mode. So this difference is likely optimized away by the Rust compiler. Dynamic BiteMuck was dropped because the static one had the same capabilities and performed just better in all cases. And the single bass backend was dropped as, according to Wasmer, it is intended for quick iteration, not for deployment, and performed strictly worse. We also use the self-referential struct version because it didn't seem to have a noticeable performance impact and is a more, is a better software design, basically. So we use that to implement all of the benchmarks for all ABIs for the macro benchmark. So for the macro benchmark results, caching continued to perform better than the non-cache version. The gap between native and WebAssembly performance closed by a couple orders of magnitude. So this performance degradation seems to largely be caused by the actual function calls into WebAssembly rather than the code being rather than the code actually running in WebAssembly. It was caused by that bridge between the two, between your host and WebAssembly environments. And the relative speed of each policy simulation was the same within each ABI. So, for example, LFU was the slowest across all 7 ABIs that we tested here. So the WASM slowdown seems to be relatively stable and not really dependent on the work that's going on inside the WebAssembly sandbox, at least in this benchmark. LLVM version performed marginally faster than the crane lift one. While policy code is more complex, it's still pretty simple, so the LLVM extra optimizations do not seem to have had much impact. Relative performance of the ABIs remained about the same. So overall, the WebAssembly slowdowns for these scripting applications are within an order of magnitude. There are more potential options for optimization, but when comparing the ABIs, it seems that these direct argument passings are preferred, which makes sense. But the BiteMuck ABI isn't much slower and still uses the pair ABI internally. And then it seems that if BinCode or protobuf could be adapted to work with a static memory allocation, then it could be a more language independent alternative to C-struct. So getting the benefits of BinCode with the performance of BiteMuck potentially. There's a lot of different ways that there could be more work into exploring Wasmer and other applications of WebAssembly. So digging deeper into the implementations of Wasmer and other runtimes to find potential optimizations, both for the hosted code, the host machine's code, as well as maybe optimizations for the library itself. Apply this with variable length data. In the future, WebAssembly is going to have its own better mechanisms for this, so exploring those as well. We could perform these tests against other WASM runtimes like WASMtime or the WebAssembly micro runtime, as well as check the performance and compatibility of these techniques with other languages like C, C++, C#, and AssemblyScript for the actual modules, just to confirm that these are more broadly applicable. Thank you. The source code for all the benchmarks is available on GitHub at the link on screen. I can put it in the Slack after, alongside with these slides. Yes, any questions? I think I heard one go off.
Thank you. Any questions? Don't see anything in Slack, but feel free to unmute yourself and ask question.
Thank you, Devon, for your interesting talk. Can I ask one question? It's in your opinion, what are the biggest difference between the benchmarking for native applications and like, for example, WebAssembly? And yeah, that's a question.
Between the benchmark for pardon what in WebAssembly?
For native applications.
Native applications.
Yeah.
I'm not sure. For WebAssembly, or for these WebAssembly benchmarks, we focus mostly on the call into the individual code rather than benchmarking. Like, we didn't measure the performance of the entire solution. We benchmarked from the call, like from the call into WebAssembly to the return. So we're trying to benchmark the, I guess, performance penalty you pay for adding this into your code base and using it to extend your application at runtime rather than the whole system performance.
Okay. Thank you for your...
I guess we had to instrument our benchmarks within the application rather than just measuring the whole runtime from the system.
Okay, thank you.
Okay, thank you very much. Then we probably could move to next one. Next one would be presented by Joseph Meyerhofer, Simplify Performance Engineering with Intelligence.
Very good. Thank you so much for the introduction. I will share my screen. One moment. Okay. I hope the sharing is working. Is my screen visual?
Yes.
Very good. Yeah, welcome everyone. My name is Joseph. I'm the founder of Performetrics, and today I'm happy to present you our Simplify Performance Engineering with Intelligence topic. Pretty much fast and reliable applications, they become more or less standard across industries. And actually what was supposed to take several years actually happened almost overnight. I'm talking about the digitalization of the customers and the businesses during the recent pandemic. And as part of this development, we see more and more performance issues popping up around the world. And Performetrics, for the last 20 years, we are taking care of performance engineering challenges. Our customers are mainly in the performance engineering space, financial area, and government industries. And we are assisting them in terms of making sure that their performance and security dreams are coming true. There's a lot of knowledge you can pick up on our blogs, and feel free to connect with me anytime. Basically, what is the motivation behind our kind of maturity model we are creating for performance engineering? Number one, we see a lot of performance challenges out there, and still customers often in the try and error mode. End users are facing performance problems. They're reporting it or simply stop using these services. Business teams are getting involved. They're doing debugging. Eventually, they come up with a kind of temporary solution, and the entire drama starts once again after the next change comes in, after they have the next change in their system. Again, the user are facing big problems in that area. The second motivation is absolutely, there are a lot of awesome tools out there for load injection, monitoring, debugging, tracing. On the other hand, we have fantastic trainings, courses. The methods are well established, shift left, workload modeling, all the stress testing and chaos engineering, but still the knowledge is not really in everywhere available. For instance, there is a missing awareness around performance engineering. Engineers have no guidance what they are doing right in their practices, for instance, and how do they need to improve for themselves. So there's still a gap. And the last motivation is, from our perspective, there's a big focus in the entire performance engineering industry on tools, but from our perspective, problem solving and communicating and creating awareness is probably more important, because if there are no requirements in place, if engineers are not skilled how to deal with complex problems and making performance engineering practices a fundamental part early in your life cycle, the most advanced tools will be kind of useless. And this is exactly the reason why we decided we create a performance engineering maturity model that roots basically on 3 core pillars. We have practices collected in the last 20 years. We have advices that are shared from industry experts. We have a kind of assessment discovery questionnaire, and at the core, a machine learning engine that is creating a remediation plan, guiding our customers what is going good and what is not so good. And the idea is really performance should not be the target. It should be more a means to an end to create awareness, efficient applications, also provide better user experience. How does our platform work? Basically, within a few minutes, everyone can do his kind of assessment, self-discovery. You will see your performance engineering rating, and you can easily compare yourself to peers, because this is very important, especially in the big businesses. They have a lot of advanced budget planning discussions going on, and if you have good arguments, maybe you can easily convince your decision makers to bring in performance engineering practices as well. And based on our experience, it helps if you, for instance, are working in the financial service industry and you can tell your leadership, oh, I'm rated like level B or C in the testing domain for performance engineering practices, but my competitors, the industry average is maybe an A or B minus, and we need to do certain things to keep up and improve our practices, basically. Number 4, once you have done your rating, you will be in a position to get a remediation plan showing you what is going good in your organization and maybe what activities must be improved. We're not focused only on the tools, but also on the practices, on the good advices. And finally, we try to build a platform where also industry experts can show their share their experience with us, so that we can use this experience in other remediations plans for other customers as well. So at the moment, if we look to the entire performance engineering industry, there are hundreds of blogs out there, a lot of trainings, but we still miss the centralization. Nowadays, engineers are very busy. They have no time to read 1,000s of blogs and books. They need a kind of intelligent way to consume this knowledge. Finally, you can go back and implement the suggested improvements. And after 6 months, usually you can do a reassessment, rate yourself and see how you're doing and whether there is still a gap compared to the industry standard. At the core of it, we have basically 3 performance engineering maturity levels. Probably at the moment, big proportion of businesses are somewhere between C and B. Either they are not really taking care of performance engineering, or maybe it's only partly integrated. There's a lot of firefighting going on. Sometimes they're more in the reactive approach towards performance engineering. And those businesses, maybe a very small pillar, they are making sure that performance engineering, performance testing, and also monitoring is part of everyone's daily job. For them, definitely they have the biggest customer benefits, and they have very mature practices in place. A couple of slides, a few screenshots from our tool. As mentioned before, we are trying to show the customer the rating in the performance maturity area. Our maturity model consists of 3 domains: build, test, and operate. Each domain has 3 practices, and each practice has another 3 discovery questions. And this is allowing us to create a kind of performance engineering maturity score for each and every practice, and also for each and every domain. So we see, for instance, for this player, they are focusing more on making sure they have strong practices in place in the operate domain, but not really advanced practices in the build area. So especially in the area of early performance analysis, they are kind of left behind. And our remediation plan would basically give them some guidance how to keep up with their competitors, how to improve their performance engineering activities. As mentioned before, I think also the comparison, the industry standards in the performance engineering space is very important. Something like this does not exist at the moment on the market. This is why we think it's absolutely required, because classic performance testing engineering consulting does not scale at all. If you look to the market, there are hundreds of openings for performance engineers, and it's really time consuming. When we educate our performance engineers, we invest almost 2 years before we assign an initial performance testing project to them. If you look to the universities, there's almost no really advanced performance engineering education in place. And I think it could really bring a lot of flexibility and also support performance engineering practice integration in many companies if companies are start using our performance engineering maturity platform, because they could learn a lot. It's a kind of central knowledge base where they could get some guidance, and especially also in the discussion around budgets and decision making. Why should I invest in the performance space? Maybe you could also use this kind of industry standard comparison to make sure that your decision makers are understanding what they are doing good and in which area they should invest actually. The remediation plan, this is only a very draft version of it. In fact, it is more complex. Here we show basically 2 examples. The first one is in the early performance analysis space. This player is rated as a C. His target is he want to get to B. And what remediation actions are required and what would be the decision makers or the customer's benefit. And this kind of hand-holding mentorship would help many businesses around the world. They probably have not enough budget to invest in hundreds of consulting days. They could easily use this performance engineering maturity platform to see how they are doing at the moment, what is not going as expected, and how do they keep up with their peers, with the industry standard, basically. Summarizing this, the benefits are definitely, we try to simplify the very complex performance engineering space. It takes very long time to learn on all the concepts. Eventually in our current situation where agile and more full stack engineers will take care of performance engineering, they need also some instruments to learn the concepts. And this is absolutely what we are trying to achieve. Number two, performance. We believe nobody should be bothered with slow running, not performing applications. So we absolutely focus on high speed, scalability, and throughput. We give companies the knowledge how to speed up their systems, what needs to be done, and how and when. Absolutely. The engineering aspect, it's absolutely important that full stack engineers get the knowledge how they can build better business applications, not always from a technical standpoint, but also from a methodical standpoint that you can only learn after you have a lot of years domain experience, or you can use our platform to get it very in an efficient, effective way. And number three, we absolutely believe that mentorship and remediation is needed along the way because performance engineering is a complex area. Probably not too many companies will afford going forward to have major performance engineering competence center of excellence. So they're looking for intelligent solutions on the market. They could guide their team, and they could also provide some transparency about how they are doing in certain areas and which areas they need to improve. Yeah, I'm on the last page. So I welcome everyone to explore our Go Benchmark platform. The basic version is for free, so you can use it, you can start the rating, you can explore it, and please share your feedback with me. And I'm interested also to hear your questions and your thoughts about performance engineering maturity model. Thank you so much for your time today.
Thank you. Hank, you have questions, so I maybe ask it yourself.
Yeah, sorry, I was looking for the button to unmute. I want to ask, so the tool looks interesting, the performance engineering, like a mentor tool. Do you provide a license for for education purposes? Like,
yes,
for example,
yeah, absolutely. Yeah, this is absolutely doable. So we have the classic version is for free, but it does not include the remediation plan. We are open to cooperate with universities, absolutely. So if you have a need to use it during your trainings and academia lessons, please contact me. I can definitely give you a voucher so you can use it for free. Yeah, no problem. Yeah.
Okay. Yeah, thank you. So this is the website, like Go Benchmark is the website.
Go Benchmark.io, correct. Yeah.
Mm-hmm. Yeah, very interesting. Thank you very much.
Very good.
And what your observation about companies that took your benchmark? So could you share your finding, kind of how many companies and what?
Yeah. So the product is almost brand new. We have started working 2 years before. We launched it on the market, I think, in March. And the reason why we are building this, we see a big scalability problem in the consulting area when it comes to performance engineering. So there are a lot of tools out there. There are trainings out there for performance engineering, but it takes a lot of time for companies to learn what they need to do and how to do it. And these two topics are exactly solved by our performance engineering maturity model, because they can kind of do their self-assessment. They see what gaps are there and how to basically solve these gaps. It's a very cost-effective way in learning. So in the last 20 years, we were working with big players in the finance industry, for instance, make sure that they plug in performance engineering practices to their entire development lifecycle and also production. And basically, in our performance engineering maturity model, we have built in all this knowledge and guide companies how to go from a current state to the desired target future state. So instead of spending a lot of consulting months, you could easily find out how you're doing it. And we have customers, they are exploring it already. The feedback is good because they tell us exactly something like that is not in place on the market. And we are absolutely not focusing on suggesting you need to use tool A, B, C, and all your problems will be solved. We are more focusing on the biggest core challenges in the performance engineering space, which is creating awareness and make sure you apply all the needed practices in your development process. Because otherwise, for instance, if you neglect performance requirements and you focus only on firefighting on production, just an example, you will have a hard time to build really a very good user experience because you're always in the firefighting mode and the users will detect issues. But yeah, it will take some time, and our idea is really also to collect advices from industry experts and use these advices also going forward when we suggest remediation plans to customers going forward as well. Does this answer your question?
Yeah. Yes. Thank you very much. Thank you very much. And we need to move to our last presentation of the day by Sean McCarthy about the work they're doing at data stacks, Fallout distributed system testing as a service.
Thank you, and hello. My name is Sean McCarthy, and I'm an engineer on the engineering productivity team at DataStax. So I'm going to be talking about our open source distributed systems test orchestration tool, Fallout, why it came into existence, its architecture, how we use it at DataStax for CI and performance analysis, what we've learned over 5 years of usage, and a review of some related work. Sorry, I've lost control of my slides. Apologies, give me just a moment here. Geez. There we are, sorry. My slides on a separate screen. Wonderful. So to start, we'll take a brief look at the motivations behind building Fallout and how it came into existence. As has been mentioned a number of times today, early performance testing and benchmarking is critical in building databases and distributed systems. The sooner we find problems, the easier and cheaper it is to fix them. There's really no point in having tests if you can't be sure that the environment is consistent and that tests are reproducible. In order to do this, we have to specify hardware, the operating system, application level settings, and of course, the details of the test workload itself. So Fallout specifies all of this information in a single YAML-based configuration file. And furthermore, we have to record as much information as possible in order to analyze possible causes of performance regressions or new bugs. Fallout captures all of this information as well. So when we say we want to run tests over and over again, we of course mean they must be automatable, either on a regular schedule or triggered by some sort of CI pipeline. Rather than reinvent the wheel, we have a REST API in Fallout that allows CI jobs and scheduled jobs in Jenkins to run Fallout tests. Manual tests are also possible and in fact necessary while developing scheduled CI tests, as well as when hunting down regressions and bugs. So 5 years ago at DataStax, we had a good but limited web-based system that could bootstrap Apache Cassandra onto an existing fixed size cluster of machines and run a linear workload that consisted of a handful of load generating tools. So we had more tools than were supported by this system, both internally and externally, which could be used to vary the provisioning of clusters and from which we could stitch together different test workloads. We needed to be able to target more environments, public and private clouds, Kubernetes, Dockers, or other areas of development. And this implied a need for something new, which would have to provide a single interface for multiple teams to run tests and benchmarking tools. Similar to the old system, it had to be configurable with simple files that described real-world systems and workloads, and had to capture and preserve test run artifacts alongside the test results. Things like log files, raw performance data, and system configuration information. Lastly, it had to be easy to use. Components had to be self-documenting, and the configuration should be declarative. So we met the configuration and declarative requirements by using a single YAML file to describe a test run and its environment. And the Fallout server provides documentation for all components and their settings in the web UI. Today, Fallout runs approximately 200 tests per day, verifying the performance of new features and optimizations, detecting regressions before we ship to customers, and reproducing any issues we find in the field. In recent years, we've added chaos testing into the mix. So let's take a look at the architecture of Fallout and the ecosystem of tools and services surrounding it. Fallout itself consists of the execution core, which is a server providing a REST API and a web client that talks to the API. The server manages the storage of test definitions as well as the artifacts generated by individual test runs. Tests are submitted via the API and placed in a queue, which allows us to fairly distribute access to our internal resources. So the execution of a single test run happens within the core in 4 distinct phases. First, we set up the environment by provisioning virtual machines or Kubernetes clusters, then configure the required software on top of that infrastructure. Next, the workload itself is executed. After the workload has completed, we copy log files and other artifacts to the Fallout server before destroying the compute resources allocated during setup. And finally, we post-process those artifacts to produce performance reports and apply various pass-fail criteria. The provisioning and configuration of the compute resources and software in Fallout is handled by multiple backend tools. For example, with Google Kubernetes Engine, we use gcloud CLI and other tools such as kubectl and Helm. For our internal cloud, we use ctool, which is an internal tool that encapsulates our years of experience installing every version of Apache Cassandra and DataStax Enterprise, as well as some more recent projects. For regularly scheduled performance tests, we aggregate performance metrics and store them in our external history server, which is a Graphite and Grafana installation. Regressions between product versions are detected using Hunter, which is our open source change point detection tool. Fallout's API allows it to act as an automation target. There's a Python-based client API and a command line interface written on top of it. The regularly scheduled performance tests are defined as matrix tests, meaning that we want to run equivalent tests across multiple versions and configurations of the software without having to repeat ourselves. This is achieved by some simple templating tools that synthesize the tests from YAML fragments. Both the fragments and the tools are kept in the Hacks GitHub repository, which also contains automation for creating scheduled Jenkins jobs for each of these tests. These jobs, in turn, use the CLI to interact with Fallout. Some of our products also interact with Fallout as part of CI through GitHub Actions or Jenkins. These tend to use the API directly as part of a PyTest framework. So having reviewed the ecosystem and high-level architecture, let's take a quick dive into the implementation of Fallout itself. So Fallout is implemented in Java, which is a widely used language at DataStax. The code's benefited from many contributions from outside of the small Fallout team over the years. As has been mentioned, test configuration is defined in YAML. There is usually a one-to-one mapping between entities specified in the YAML configuration and an instance of a Java class. The test definition is composed of 2 sections: the ensemble, which defines the test environment, and the workload, which defines the steps of the test itself. So looking at the ensemble, we have sets of virtual machines and Kubernetes clusters represented by an ensemble of node groups. So a node group is a cluster of nodes. A node is a single virtual machine instance. Additionally, node groups are assigned roles, one per node group. For example, the server is the system under test, commonly an installation of DataStax Enterprise, Apache Cassandra, or recently Apache Pulsar. The client is a workload generating system. There can be multiple server and client node groups each. We also define an observer, which is a node group hosting performance metric capture endpoints such as Prometheus, Victoria Metrics, or Graphite. And finally, we have a controller, which is a virtual node group representing the Fallout server itself, which is, of course, part of the system, issuing commands to the server, client, and observer node groups during the test workload. Node groups and nodes are acted upon by provisioners and configuration managers. Node groups are created and destroyed by a provisioner, implying, of course, that there is only one provisioner per node group. For example, we have a GKE provisioner that creates and destroys Kubernetes clusters in the Google Kubernetes engine. Software is installed, configured, started, and stopped on a node group by configuration managers. There should be one configuration manager per software product, meaning that we have multiple configuration managers per node group. The software installed by configuration managers can be both the system under test, for example, Apache Cassandra, or the load generating benchmark tools, commonly NoSQL Bench. Node groups have a lifecycle encapsulated by state changes. Each node group has a state which changes during this lifecycle. We have a state machine which decides whether to apply an action from a provisioner or a configuration manager onto a node group as a function of the current state and desired state. Also, the current state is detected at runtime if we don't know what it is, which allows us to reuse node groups between test runs. The workload defines the actions performed by and against the ensemble. Is split into 3 stages. The first stage is a set of module executions where a module is essentially a single unit of work. These can run sequentially or in parallel. Once all the modules have finished execution, we run checkers. These are intended to analyze a history log reported by module executions and return pass-fail criteria based on the content of that log. We also have artifact checkers, which examine any artifacts captured by Fallout, perform post-processing, and also produce pass-fail signals. So modules encapsulate operations on the ensemble. There are load-generating benchmarks, such as NoSQL Bench and Cassandra Stress. There are also modules for generating failures in the ensemble, for example, Chaos Mesh. So there are many modules, but one lesson we've learned is that there has to be an escape hatch to allow users to quickly define their own operations, which is why we have a bash module, or in Kubernetes we also have a kubectl module. Modules perform operations using providers. These are installed during the setup steps by provisioners and configuration managers. Providers define the services available. So because modules define what providers they require and provisioners and configuration managers define what providers they install, we can validate a test definition before running it. For example, the NoSQL Bench module requires a NoSQL Bench provider, which will be installed by the NoSQL Bench configuration manager. So if a user tries to use the NoSQL Bench module without having declared the NoSQL Bench configuration manager, we can throw a validation error during test submission and prevent the user from spending too much time iterating on a test. So as mentioned, checkers can look at the module history, which records results of whether modules had any errors during execution. Most commonly used is the no-fail checker, which ensures that no errors occurred during benchmarking. Typically, an error during load generation is likely to invalidate results. Artifact checkers can check through the retrieved artifacts. One often used is the system log checker, which searches for errors in the Apache Cassandra system log. There are also artifact checkers to perform post-processing. The HDR tool aggregates load generator high dynamic range histogram performance metrics retrieved from client metrics. And once we have these performance metrics generated by one or more test runs, we typically visualize and analyze the results. So Fallout can directly generate performance reports from client performance metrics gathered in the form of these HDR histogram time series data. The HDR tool artifact checker, as well as doing the previously mentioned task of aggregating the histograms, also produces an interactive HTML report visualizing the data. Data captured across multiple test runs can be captured as well. And these reports are available as permalinked URLs on a Fallout server, which allows us to link reports showing improvements or regressions from Jira tickets and refer back to these reports when benchmarking new work or troubleshooting new issues. Another performance analysis tool is the history server. This is a Graphite and Grafana installation that stores aggregated metrics created by the HDR tool, hosted to the Graphite instance by Fallout when triggered by packs. They're used to track the aggregate performance of a product against specific test scenarios across successive development versions. So sort of tracking the day-over-day development, the day-over-day change in performance as development goes on. Storage is very efficient thanks to an aggressive Graphite retention policy. As an example, here's one of our history server dashboards. So Fallout has changed over the years, and some of the main lessons we've learned are that configuration of files should be short and expressive. Short definitions are clear and will have fewer mistakes. We've tried to optimize for common usage by choosing sensible defaults for Fallout components. Templating for configuration files encourages reuse. Originally running a test against, for example, Apache, Cassandra 3.11 and 4.0 would require copying the entire definition just to change one line. So we've added support for mustache templates, which allow sections of a definition to be varied when running a test. Tests often need access to external files. Originally, when a module, for example, would need access to one of these external files, such as a NoSQL bench workload, the module would have to retrieve the file from an external URL. This led to a fragmentation of test definitions, so we introduced local and remote file management mechanisms to allow external files to be defined within the test definition in a variety of ways, most commonly as a resource within a GitHub repository, or also located at a URL, or often defined inline in the test definition in various formats. So long-running tests benefit from semantic checks and item potency. Iterating on a test definition can quickly become painful if simple errors are only reported during test execution. So over the years, we've improved on static validation performed on test definitions. Also, since the setup of node group can take some time, the node group lifecycle allows us to detect already running clusters and skip the setup steps. So automated testing, which includes running benchmarks, is a vital part of ensuring quality for our software projects. Fallout is not the first nor last project to take on this role. Some other projects include MockFog 2.0, Adelphi, the distributed systems infrastructure produced by MongoDB, and some others detailed in our paper, but just today, right? The CTT Tosca system presented by Thomas. We've detailed some more systems in our paper. So many people have contributed to Fallout success at DataStax. I'm running out of time, so I'm just going to kind of list all of them here. Like I said, being a Java project, it really has benefited from many interested parties making contributions to Fallout itself, as well as the surrounding ecosystem. So with that, thank you for your time. If there are any questions, I'll be happy to address them.
Alex, I think you're muted, Alex.
Thank you. Are all these parts proprietary, developed at DataStax, or you use some kind of generic open source tools or some kind of commercial tools?
It's a combination. So the Fallout core, the server, the node group lifecycle, the workload execution has all been open sourced. There are internal components such as ctool, which is still proprietary, largely due to its connection to a lot of our internal infrastructure. But Fallout relies heavily on a lot of different open source projects. For example, gcloud, Helm, Cube Control, Minikube, really lots of others. As we look towards integrating more and more different systems and environments, the plan is to have most of this be based on the existing open source tool. and for this to be included in the open source version of Fallout.
I could ask a quick question. Like, in distributed systems, there are so many nodes with different configurations, probably, and they handle different number of requests. So how do you aggregate those different performance metrics from different machines serving different number of requests?
Sure. So, for example, if we have a test with 2 separate NoSQL bench clients, each client is going to produce a set of these HDR artifacts. And the HDR artifacts are histogram reservoirs with timing information. So we can pull down both sets of artifacts to the Fallout server, and the HDR tool will ingest both sets of HDR artifacts, line up each reservoir on the timing information, and then combine the population samples, right? These latency throughput responses within each time window into a single set to sort of unify that view of the client behavior against the system.
Okay, thank you. Thank you.
Yeah. Any more questions? Okay, so thank you very much. We had a great program today. Thank you very much for all presenters. It was really great presentation. We cover a lot of interesting topics. Again, for authors, please upload, post your slides to Slack. So we plan to post all that information to our website, probably slides. I hope that we will have recording, so we'll post recording. So I hope that it will be all available and many more people would enjoy that content, because looks like Sunday was not the best idea to have it. And big thanks to my co-organizer, Hank and Nima, which did huge work preparing all that. And again, thank you to all. Thank you, authors, attendees. We had great discussion of almost for every presentation.
Thank you very much.
And thank you, Alex, for helping and doing all of the hard work for us.
Yeah, and tomorrow it's ICP proper, so hope to see you there.
And thank you, Hank, for everything that you've done.
Thank you, everyone, and see you around, I think.
Yeah. So much.
ICP.
It's very good. Wish you a good evening. A good day, yeah.
Bye.
Thank you. Goodbye.
Take care. Bye-bye.
Bye-bye.
Thank you.